Have you ever stood outside on a perfectly clear night and looked up at the vast canopy of stars stretched out above you? That shimmering band of light we call the Milky Way is not just a beautiful backdrop for our evenings, it is our home galaxy, a swirling collection of over 100 billion stars, countless planets, and mysteries so profound they challenge everything we think we know. For centuries, humanity has gazed upward with a mix of awe and curiosity, mapping constellations and tracing the paths of familiar celestial bodies. Yet, for all our progress, the deeper we peer into the cosmic dark, the more we realize how much remains hidden, waiting just beyond the edge of our understanding. Today, we're setting out on a journey to explore some of the most perplexing enigmas tucked away in our own galactic neighborhood. From invisible forces tugging at the fabric of space to unexplained lights flickering in the void, the Milky Way is filled with objects so strange, so baffling, they seem to defy the laws of physics as we know them. These aren't just abstract concepts discussed in scientific papers, they are real, tangible mysteries that spark our imagination and invite us to question what is possible. What if I told you that some of these cosmic anomalies might hold clues to the nature of dark matter, the birth of black holes, or even the possibility of life in forms we can scarcely conceive? In this video, we'll uncover 30 of the most bizarre and fascinating objects ever detected within our galaxy. Each one tells a story, a piece of a puzzle that astronomers and scientists around the world are working tirelessly to solve. We'll venture into regions where time and space behave in unbelievable ways, examine celestial phenomena that challenge our definitions of reality, and perhaps even catch a glimpse of the unknown forces quietly shaping the universe around us. So settle in, open your mind to the extraordinary, and join me as we dive deep into the wonders and mysteries hiding in plain sight, right here in our cosmic backyard. Our journey into the unknown begins not with a flash of light or a swirling vortex, but with an invisible, relentless pull. Imagine you're in a boat on a vast, calm river, drifting gently but unmistakably in one particular direction, even though there's no wind. Now scale that feeling up to a galactic level. For decades, astronomers have known that our Milky Way, along with our entire local group of galaxies, is not floating aimlessly through space. We are all moving, being pulled at an astonishing speed of over 600 kilometers per second toward a specific point in the cosmos, a mysterious, unseen force so powerful it defies easy explanation. This is our first strange object, the Great Attractor. The mystery deepens when we try to look directly at it. This colossal gravitational anomaly lies in the direction of the constellation Centaurus, but it is hidden from our view by the dense bulge of stars, gas, and dust at the very heart of our own galaxy. Astronomers call this region the zone of avoidance because the Milky Way's central plane effectively blocks our sight, like trying to peer through a thick, dusty fog. For a long time, this cosmic camouflage left scientists with a profound puzzle. What could possibly possess enough gravity to tug on entire galaxies, yet remain completely invisible to our telescopes? Early theories suggested it might be an immense concentration of mass, perhaps a massive cluster of galaxies we simply couldn't see. As our technology advanced, allowing us to peer through the cosmic dust with infrared and radio telescopes, we began to glimpse the truth. We discovered that the Great Attractor is indeed part of a much larger structure, a gravitational cornerstone in our cosmic neighborhood known as the Laniakea supercluster. Our Milky Way resides on the very outskirts of this immense web of galaxies, which spans over 500 million light-years. The Great Attractor acts as the gravitational center of this supercluster, the central point toward which everything is slowly flowing. But even with this discovery, the nature of the Great Attractor itself remains a topic of intense study. Is it primarily the work of a tremendously massive cluster of galaxies like the Norma cluster sitting at its heart? Or does its incredible pull hint at the influence of something even more exotic, like vast clouds of dark matter, the unseen material that makes up most of the universe's mass congregating in a single, dense node? The truth is likely a combination of both, a conventional, albeit huge, collection of galaxies amplified by the irresistible grip of dark matter. This enigmatic region reminds us that even the largest structures in our universe are governed by forces we are still striving to fully comprehend, a silent, powerful reminder of how much lies hidden in the darkness. Leaving behind the immense hidden pull of the Great Attractor, we now travel inward toward the very heart of our galaxy. Here, buried within the bright, chaotic core of the Milky Way, lies a monster, Sagittarius, a star, a supermassive black hole with a mass 4 million times that of our Sun. It is a place where the laws of physics are pushed to their absolute limit, a gravitational vortex from which not even light can escape. And it was here that astronomers witnessed an event they thought they understood completely, only to have their predictions turned upside down by a strange and resilient object known as the G2 cloud. The story began in 2011, when astronomers tracking the region noticed a peculiar, elongated cloud of gas, 3 times the mass of Earth, on a collision course with oblivion. Its path was a highly eccentric ellipse, and calculations showed it was headed straight for a close encounter with Sagittarius, a star. The scientific community braced for a spectacular cosmic show. The prevailing theory was straightforward and brutal. As the cloud approached its point of closest approach, or periapsis, the incredible tidal forces from the black hole, the difference in gravity between one side of the cloud and the other, would stretch and tear it apart completely. This process, called spaghettification, would pull the cloud into a long, thin streamer, feeding the black hole a sizable meal and creating a bright flare of radiation as the gas heated to millions of degrees in its death throes. Telescopes around the world were pointed at the galactic center, waiting for the inevitable fireworks. The year of its closest approach, 2014, came and went. The cloud reached its periapsis and nothing happened, or at least not the dramatic destruction everyone had anticipated. The G2 cloud was indeed stretched and deformed by the black hole's gravity, but it survived the encounter largely intact. It didn't completely dissipate, it slipped past the point of no return and continued on its orbit. It was as if a wisp of smoke had passed through a typhoon and somehow failed to disperse. This incredible defiance of expectations sent astronomers back to the drawing board and sparked a fascinating debate. How did a simple cloud of gas possess the structural integrity to withstand the most extreme environment in our galaxy? The most compelling explanation suggests that the G2 cloud was never just a cloud. To survive that encounter, it must have had some kind of internal anchor, a denser, more massive core that held it together against the black hole's gravitational shear. The leading theory proposes that at the heart of this gas cloud was a star, perhaps a very young one still shrouded in its natal cocoon of gas and dust, or a binary star system that had recently merged, releasing a shell of material that was now being pulled along by the hidden stellar object within. This massive central object would provide the gravitational glue, preventing the entire structure from being instantly ripped apart. It's a cosmic case of a nut hiding inside a fluffy shell. The black hole could nibble at the shell, but it couldn't crack the nut open. This event did more than just present a puzzle. It provided an unprecedented experiment. The way the cloud stretched and interacted with the black hole's accretion flow gave scientists a unique probe to study the conditions and the magnetic fields around Sagittarius, a star itself. The object's resilience forced a re-evaluation of what can exist and survive in the violent downtown of our galaxy, suggesting that stars can and do form in remarkably hostile environments. The mystery of the G2 cloud reminds us that even around a known monster, the universe is full of surprises, challenging our models and inviting us to look closer at what we think we already understand. Yet, as we move our gaze from the immediate violence surrounding the black hole to the broader structure of our galaxy's heart, we find a different kind of mystery, one not of chaotic survival, but of astonishingly precise symmetry. The central bulge of the Milky Way, that dense, football-shaped collection of ancient stars surrounding Sagittarius, a star, has long been thought to be a somewhat simple, albeit massive, structure. But when astronomers finally managed to peer through the obscuring dust and map the stars within it in detail, they discovered something that should not, according to many models, be there: a giant cosmic X. This discovery didn't come from a single dramatic image. Instead, it was painstakingly pieced together through the work of space telescopes like the Wide Field Infrared Survey Explorer, or WISE. Infrared light is key because it can penetrate the thick clouds of dust that block our visible light view of the galactic center. By carefully counting and mapping the distribution of millions of individual stars within the bulge, scientists began to notice a peculiar pattern. The stars weren't arranged in a random or smoothly elliptical blob. They were distributed in a distinct X-shaped structure, as if the heart of our galaxy was stamped with a vast stellar signature. So how does a galaxy end up with such a perfectly peculiar shape at its core? The leading theory takes us back to the very nature of our galaxy's form. The Milky Way is not a perfect spiral. It is classified as a barred spiral galaxy, meaning it has a central bar structure made of stars, gas, and dust that cuts through its center. The current thinking is that this X shape is a natural but fascinating byproduct of that central bar. Imagine a thick bar of stars spinning within the galaxy. Over immense periods of time, the gravitational instabilities within this rotating bar can cause it to buckle and thicken vertically, much like how a pizza chef might toss and spin dough, causing its center to puff up. In some models, the orbits of stars within this buckling bar can become unstable, causing them to move in trajectories that create this distinctive X-shaped distribution when viewed from the side. The presence of this X is more than just a curiosity. It's a crucial piece of evidence in understanding the formation and evolution of our entire galaxy. It tells us that the central bar of the Milky Way is fundamentally unstable and has likely been buckling and evolving over billions of years. This dynamic process helps explain how stars and energy are redistributed within the galactic center, influencing the growth of the bulge itself and even the activity around the central black hole. Seeing this structure confirms that our galaxy's core is not a static, ancient relic, but a dynamic and evolving environment, its shape carved by the relentless pull of gravity acting over cosmic time. To truly appreciate its scale, modern astronomers have used the vast troves of data from surveys like WISE to construct stunning three-dimensional models. These models allow us to fly through the galactic bulge and see the X structure from all angles, revealing it as a truly three-dimensional phenomenon, not just a two-dimensional pattern on the sky. It's a subtle structure, visible only when you look at the collective arrangement of countless stars, a ghostly imprint of the Milky Way's dynamic history written in the language of stellar orbits. This cosmic insignia, hidden within the brightest and most crowded part of our galaxy, stands as a quiet testament to the beautiful and complex physics that sculpt the universe, often in forms of startling and simple geometry. But the marvels of our galaxy's core are not confined to the stars and structures we can see. Emanating from this violent, dynamic center are two colossal, invisible structures that dwarf everything else we've discussed, stretching over half the visible sky yet completely undetectable to human eyes. These are the Fermi Bubbles, two vast lobes of superheated gas and energetic radiation ballooning outward from the galactic center, one above and one below the plane of the Milky Way. To grasp their scale, imagine a structure so immense that it takes light 25,000 years to travel from its base at the black hole to the top of one bubble, a total height of 50,000 light-years. Our entire solar system and every star you've ever seen in the night sky sits nestled within the lower reaches of this invisible cathedral. For such enormous structures, their discovery was remarkably recent and somewhat accidental. They weren't found by peering through an optical telescope, but by sensing the universe's most energetic light, gamma rays. The Fermi Gamma Ray Space Telescope, launched in 2008, was designed to scan the entire sky for these high-energy photons, often associated with the most violent events in the cosmos. As scientists began to analyze its data, they noticed something perplexing. There was a persistent, diffuse glow of gamma rays, and it was shaped not like a random cloud, but like a distinct, symmetrical figure 8 centered perfectly on the core of our galaxy. It was as if two gigantic orbs were inflating from the center, extending far into the galactic halo. This was the first clear evidence of the bubbles, a discovery that fundamentally altered our understanding of the Milky Way's activity and history. The immediate and pressing question was, and still is, what created them? How does a galaxy forge such perfectly symmetrical, unimaginably large structures? The prime suspect, perhaps unsurprisingly, is the supermassive black hole Sagittarius A star. The leading theory suggests that at some point in the past, the black hole experienced a period of tremendous activity, a feeding frenzy on a scale we can barely comprehend. As vast amounts of matter spiraled into the accretion disk, not all of it crossed the event horizon. Instead, a portion of this incredibly heated gas and magnetic energy was funneled and launched away from the poles of the black hole at near light speed, erupting into space as two opposing jets of relativistic plasma. These jets would have plowed through the halo gas of the galaxy, inflating these massive bubbles and filling them with energetic particles that continue to emit gamma rays millions of years later. But the black hole isn't the only possible sculptor. Another compelling hypothesis points to a frenzy of a different kind, a starburst event. This theory proposes that there was a time when the galactic center was forming new stars at an absolutely ferocious rate. With so many massive stars being born in a crowded environment, they would have lived fast, died young, and exploded as supernova in quick succession. This chain reaction of violent stellar deaths could have generated a powerful, isotropic wind, a superheated shockwave exploding outward in all directions from the core. This galactic scale wind would have blown the surrounding gas outward, carving the very same bubbles we see today. The evidence is still being gathered, and the true answer might even be a combination of both events, a dual cataclysm of black hole activity and stellar fireworks working in concert. What makes the Fermi Bubbles so captivating is that they are a fossil record of a dramatic, violent chapter in our galaxy's life that occurred sometime between 2 and 4 million years ago. They are a lingering echo of an eruption so powerful it reshaped the galactic environment around us. Their continued existence tells us that our galaxy is not a quiet, stable place, but a dynamic system capable of phenomenal outbursts that reverberate for eons. They serve as a colossal reminder that even our home galaxy has a tempestuous past, and that the greatest structures in the cosmos can often be hidden in plain sight, waiting for the right technology to reveal their magnificent and terrifying forms. After witnessing the colossal, energetic structures that define our galaxy's center, we now turn our attention to a strange and solitary traveler on a long journey home, an object that tells a different kind of story about our galaxy's violent and acquisitive nature. High above the galactic plane, a massive, invisible cloud of hydrogen gas is streaking toward the Milky Way at nearly 300 kilometers per second. This is the Smith Cloud, a celestial wanderer discovered entirely by accident, and its story challenges our understanding of how galaxies gather new material and even how they might recycle their own. Its discovery dates back to 1963, when a young astronomy doctoral student named Gail Smith was analyzing data from a Dutch radio telescope. She was studying the intense radio source known as Cassiopeia A, the remnant of a supernova explosion, but in her data, she noticed something else entirely, a faint, diffuse radio emission that seemed to move across the sky. This emission was the signature of neutral hydrogen gas, and it revealed a vast cloud over 10,000 light-years long and 3,000 light-years across, containing enough gas to form over 2 million suns. For decades, its origin remained one of astronomy's quiet mysteries. Was it a cloud condensing from the pristine hydrogen of intergalactic space, a remnant of a small galaxy torn apart by our own, or something else entirely? The cloud's trajectory is its most compelling feature. Detailed observations from instruments like the Green Bank telescope have mapped its path with incredible precision. We now know the Smith cloud is not just moving near our galaxy, it is on a direct collision course. In approximately 30 million years, it will plow into the Milky Way's disk, specifically into a spiral arm in the constellation Perseus. The event will be a spectacular, slow-motion celestial firestorm. The immense pressure of the impact will trigger a burst of star formation, compressing the galactic gas and dust it slams into, likely giving birth to countless new, brilliant stars. It's a delivery of raw building materials on a galactic scale, a gift of creation wrapped in a package of destruction. But this journey raises a critical question. How has this enormous, diffuse cloud of gas managed to stay intact? The space between galaxies is not entirely empty. It is filled with a thin, hot gas known as the galactic corona. For the Smith cloud to have traveled from wherever it came from, it would have had to plow through this coronal gas, an experience that should have ripped it apart and dissipated it long ago. The fact that it remains a coherent structure suggests it must have some form of invisible armor, a protective magnetic field or a gravitational anchor holding it together. This resilience is a major clue pointing toward its origins. The leading theory now suggests the Smith cloud is not a pristine, first-time visitor but a returning exile. Spectroscopic analysis revealed a crucial detail. The cloud is not composed of the pristine hydrogen and helium that existed before the first stars. Instead, it is enriched with heavier elements like sulfur, which are forged in the hearts of stars and scattered across space by supernova explosions. This means the gas in the Smith cloud has already been processed inside our galaxy. It was likely originally ejected from the Milky Way's disk by a tremendous event, perhaps a powerful supernova or a cluster of them, which blasted this material high into the galactic halo. Now, after a long journey lasting perhaps 100 million years, gravity is pulling this galactic fountain spray back down, returning it to the disk from whence it came to be used again in a new generation of stars. This incredible cycle reveals a galaxy that is not just a collector of matter, but a recycler of it, breathing out its own material only to draw it back in again eons later. Leaving behind the epic galactic-scale drama of the Smith cloud, we now turn our attention to a discovery that reminds us that you don't need a PhD or access to a multi-million-dollar observatory to make a profound contribution to science. Sometimes all you need is a curious mind and an internet connection. This is the story of Hannes Voorwerp, a strange, glowing green cloud in space, and the school teacher who found it, forever changing our understanding of quasars and showcasing the incredible power of citizen science. The year was 2007, and a new online project called Galaxy Zoo had just launched. Its goal was a monumental one, to classify the shapes of nearly 1 million galaxies from the Sloan Digital Sky Survey. Computers at the time were notoriously bad at this task, often misidentifying spiral arms or elliptical blurs, but the human brain is exquisitely wired for pattern recognition. The project's founders hoped a few dedicated volunteers might help. They were overwhelmed when over 150,000 people from all around the world enthusiastically joined the effort, clicking through image after image, categorizing the universe from their home computers. Among them was Hanny van Arkel, a primary school teacher from the Netherlands. She was spending her free time classifying galaxies when she stumbled upon an image that was unlike any other. There, next to a typical-looking spiral galaxy known as IC 2497, was something utterly bizarre, a bright, irregular, and distinctly green cloud of light. It had no stars, no discernible structure, just a luminous, ghostly blob. Intrigued, she flagged the image in the Galaxy Zoo forum with a simple note asking, "What is this?" The message included the Dutch word voorwerp, which simply means object, and so Hanny's voorwerp, Hanny's object, was christened. The astronomical community was immediately captivated. What was this thing? Follow-up observations with the largest telescopes on Earth, and eventually the Hubble Space Telescope, revealed its true nature. The voorwerp was a massive cloud of gas, billions of times the mass of our Sun, but it wasn't generating its own light. Instead, it was acting like a colossal neon sign, fluorescing under an intense, invisible energy source. The cloud was glowing with a specific, vivid green hue characteristic of ionized oxygen, a telltale sign that it was being blasted by an enormous amount of ultraviolet radiation. The source of that radiation was the key to the mystery. The spiral galaxy next door, IC 2497, contains a supermassive black hole at its core. The leading theory posits that in the relatively recent past, this black hole was a brilliant quasar, a cosmic lighthouse shining with the light of a trillion stars as it voraciously consumed surrounding matter. This quasar emitted a beam of intense radiation so powerful that it lit up the voorwerp cloud, which sits tens of thousands of light-years away from the galaxy, like a celestial spotlight illuminating a distant fog bank. But by the time Hanny van Arkel found it, the quasar had gone quiet. The light we see from the voorwerp is a light echo, a delayed message from a cataclysm that has already ended. We are seeing the aftermath of the beam's journey, the lingering glow of gas that is still responding to a scream from the past that has since fallen silent. This discovery was transformative. It provided a rare and valuable time-lapse view of a quasar's life cycle, demonstrating that these monstrous engines can switch off on a human timescale, relatively speaking. The quasar in IC 2497 likely consumed all the readily available fuel in its immediate vicinity, causing its brilliant accretion disk to dim and leaving behind a silent black hole. Hanny's voorwerp is the fading evidence of its former glory, a cosmic fossil that allows astronomers to study the conditions and the power of a quasar outburst long after the central engine has shut down. It stands as a permanent testament to the fact that the most curious minds can be found anywhere, and that sometimes the most extraordinary discoveries are waiting to be found by anyone willing to look. From the galactic recycling of the Smith cloud and the serendipitous discovery of Hanny's voorwerp, we now journey to a group of enigmatic objects much closer to home, hiding in plain sight within our own cosmic neighborhood. They are known as the Magnificent Seven, and despite their name, they are not heroes in a Western film, but a collection of some of the most peculiar and misunderstood neutron stars ever discovered. Neutron stars themselves are the incredible, ultra-dense corpses of massive stars that have gone supernova. A typical neutron star packs more mass than our Sun into a sphere no wider than a city, making them some of the densest objects in the universe. We often detect them through two primary methods: by their rhythmic pulses of radio waves, if they are pulsars, or by the intense X-rays they emit as they pull material from a companion star. The Magnificent Seven, however, defy these expectations. Discovered piecemeal by X-ray observatories like Rosat and later studied in depth by Chandra and XMM Newton, these seven objects are all within a few thousand light-years of Earth. They are incredibly bright in X-rays, shining with a soft, thermal glow that suggests a scalding hot surface. Yet, when astronomers pointed radio telescopes toward them, they were met with utter silence. They are not pulsars. Even more puzzling, they appear to be completely alone in space, with no binary companion star in sight to explain what is heating them up so dramatically. This presented a profound mystery. A solitary neutron star should, over millions of years, cool down and fade from view. The Magnificent Seven, however, are anything but cool. Their surfaces are estimated to be blazing hot, around 1 million degrees Celsius. Without a companion star to feed from, what source of energy could possibly be keeping them so intensely hot for so long? The leading theory points to their magnetic fields, but not in the way you might expect. While all neutron stars have immensely powerful magnetic fields, the Magnificent Seven might be a special class possessing what are called ultra-strong magnetic fields. These fields could be so incredibly powerful that they are actually altering the very physics of the star's interior and crust. One hypothesis suggests that these mega fields are slowly decaying over time, and as they do, they release a tremendous amount of energy directly into the star's crust, essentially acting as a built-in furnace that reheats the surface and produces the brilliant X-ray glow we observe. Another fascinating possibility involves a concept known as the neutron star atmosphere. It's thought that a particularly strong magnetic field can trap a thin layer of light elements like hydrogen or helium on the star's surface. This captured atmosphere could then act as a blanket, efficiently insulating the star and slowing its cooling process to a crawl, allowing it to retain its youthful heat for far longer than any standard model would predict. Alternatively, some researchers propose these objects might be accreting from the extremely thin interstellar medium, the wisps of gas and dust that float between stars. While this intergalactic breeze is incredibly faint, the immense gravity of a neutron star could be enough to gather and compress these trace particles. As this minuscule amount of material slowly drifts onto the surface, it would impact with such force that it releases energy in the form of X-rays, providing a steady, if very weak, trickle charge that keeps the star shining. The ongoing study of the Magnificent Seven is a brilliant example of how astronomy often works. A discovery is made that doesn't fit the established categories, forcing scientists to re-examine their models and expand their understanding of what is possible. These seven lonely, hot objects are cosmic laboratories, offering a unique window into the extreme physics of magnetic fields, particle behavior, and heat dynamics under conditions we could never hope to replicate on Earth. They remind us that even the most well-understood classes of objects in the universe can hold extraordinary secrets, proving that sometimes the greatest mysteries are not the most distant, but those that have been quietly residing next door all along. Our exploration of the Milky Way's strangest objects now takes us beyond its shimmering spiral arms and into the vast, dark halo that surrounds it. Here, we expect to find a swarm of small, ancient dwarf galaxies, each a fossil from the universe's earliest days, orbiting our own in a random, chaotic dance. This expectation is a cornerstone of our leading model of the cosmos, known as the Lambda-CDM model. But what astronomers actually found was so bizarre, so seemingly orchestrated, that it has sparked a serious crisis in cosmology. Many of these satellite galaxies are not moving randomly at all. Instead, they are aligned with breathtaking precision, tracing out a colossal, thin, and rotating disk that encircles the Milky Way like a vast cosmic carousel. This discovery is profoundly unsettling because it directly contradicts a fundamental prediction. In the Lambda-CDM model, which posits a universe dominated by cold dark matter and dark energy, large galaxies like our Milky Way form through the hierarchical merging and accretion of countless smaller structures. The dark matter halo that forms from this process should be roughly spherical, and the dwarf galaxies that fall into it should retain their own random orbits, arriving from all different directions over billions of years. Finding them all neatly arranged in a single, coherent plane that is also rotating a structure astronomers call the vast polar structure is akin to throwing a handful of gravel into the air and watching it somehow arrange itself into a perfect spinning ring. It simply shouldn't happen. This anomaly has forced cosmologists to re-examine their most basic assumptions, leading to two fiercely debated schools of thought. The first and most dramatic possibility is that this disk is a primordial structure, a fossil from the formation of the Milky Way itself. This theory suggests that the dwarf galaxies and the globular clusters within this plane were not all independent entities that were captured, but were instead born together from a single, massive cloud of gas that collapsed in the early universe, forming this coherent disk long before the Milky Way's spiral structure even took shape. If true, this would mean our standard model of galaxy formation is missing a crucial piece of physics, perhaps related to how gas flows and condenses in the presence of powerful magnetic fields in the early universe. The second major theory offers a more recent and perhaps more violent explanation. It posits that this astonishing alignment is not primordial but the result of a colossal tidal interaction. The proposed culprit is the most massive galaxy group near us, the Andromeda Galaxy and its own entourage. The hypothesis suggests that billions of years ago, a large group of dwarf galaxies may have been orbiting Andromeda. During a close encounter between the Andromeda group and our own nascent Milky Way, the immense tidal forces could have ripped this group apart, shearing it into a long, coherent streamer of galaxies. This stream would then have been captured by the Milky Way's gravity, settling into the thin, rotating disk we observe today. This would make the structure not a native feature of our galaxy, but a cosmic trophy from an ancient clash of titans. Scientists use incredibly sophisticated 3D orbital simulations to test these ideas, running the clock backwards and forwards on the motions of these dwarfs to see which scenario best fits their current positions and velocities. While the tidal scenario can produce a disk-like structure in some simulations, matching the precise thinness, coherence, and direction of rotation observed remains a significant challenge for the models. This persistent difficulty is what keeps the debate so alive and the mystery so compelling. The disk of satellites is more than just a curious alignment. It is a direct observational challenge to our understanding of the universe's fundamental architecture, a silent, spinning ring of evidence that the dark cosmos might be far more structured and organized than we ever dreamed. Continuing our journey through the ghostly imprints of our galaxy's past, we arrive at the scene of a truly ancient crime, one that has left its evidence scattered across the sky in the form of billions of stars. This is the story of the Gaia sausage, the remains of a dwarf galaxy that had the catastrophic misfortune of colliding with the nascent Milky Way some 8 to 11 billion years ago. Its discovery is a testament to modern astronomy's power to read the subtle motions of stars like a cosmic history book, revealing a violent event that fundamentally shaped the galaxy we call home today. For centuries, the galactic halo, the vast spherical cloud of ancient stars and globular clusters surrounding the Milky Way's bright disk, was thought to be a relatively quiet and random place. Then, the European Space Agency's Gaia spacecraft began its mission. Gaia is not just any telescope. It is a precision astrometric instrument designed to map the positions, distances, and motions of over 1 billion stars in our galaxy with unprecedented accuracy. It is essentially creating the largest and most precise 3D map of our cosmic neighborhood ever made. As this incredible trove of data began to stream back to Earth, astronomers started to notice something peculiar. They weren't just seeing random stellar motions, they were seeing patterns, streams of stars all moving together in a way that hinted at a shared, violent origin. The most stunning pattern to emerge was a specific group of stars, all moving in highly radial, plunging orbits. Unlike the orderly, circular orbits of stars in the Milky Way's disk, these stars were moving like comets on steroids, hurtling in on extremely elongated paths that took them diving deep into the galactic center before soaring back out into the distant halo. When scientists plotted the velocities of these stars, the data points didn't form a scattered cloud. They clustered into a distinct, sausage-like shape in the velocity graph. The name, while humorous, is perfectly descriptive, the Gaia sausage. This bizarre orbital signature was the unmistakable calling card of a major galactic merger. The theory suggests that in the early universe, a sizable dwarf galaxy, perhaps as massive as several billion suns, was on a collision course with our own. It didn't just pass by, it plunged directly into the heart of the primordial Milky Way in a head-on collision. The immense gravitational forces during this merger would have completely shredded the smaller galaxy, pulling its stars away from each other and scattering them throughout our galaxy's halo. Yet, physics dictates that these stars would retain the momentum and direction of their original parent galaxy. Even after billions of years, they still move in concert, their elongated orbits preserving the memory of that fatal dive. The Gaia sausage isn't just a collection of stars, it's the fossilized trajectory of an entire galaxy's destruction. The impact of this discovery extends far beyond just identifying an ancient wreck. This colossal merger is now believed to have been one of the most significant events in the Milky Way's history. The energy from the collision is thought to have played a crucial role in forming the galaxy's thick disk, the puffier, older component of our galactic plane that surrounds the thinner, younger disk our Sun resides in. Furthermore, astronomers now suspect that the central black hole of this ill-fated dwarf galaxy, known as the Sausage Galaxy, did not disappear. Instead, it likely merged with the Milky Way's own central black hole, potentially contributing a significant chunk of mass to Sagittarius, a star. The sheer number of stars contributed by this single event is staggering. It's estimated that the sausage may account for a significant portion of the stellar population in the inner galactic halo, with perhaps 50 billion stars or more originally belonging to this doomed system. Gaia's data visualizations bring this ancient drama to life. By applying filters to the data to isolate stars with these specific radial velocities, astronomers can create stunning 3D maps that show the sausage stars not as a coherent structure, but as a diffuse swarm, their orbits all pointing like arrows toward the same central point, tracing the path of their long-vanished home. This discovery has fundamentally rewritten the early chapters of our galaxy's biography, revealing a past far more violent and dynamic than we ever imagined. It shows us that the Milky Way did not grow gently, but through a series of colossal acts of cosmic cannibalism, with the Gaia sausage standing as one of its largest and most formative meals. Venturing beyond the halo and its orbiting dwarfs, we now set our sights on a starkly different kind of cosmic structure, one defined not by what is there, but by what is conspicuously absent. Imagine the largest emptiness you can, a void so profound and so vast it defies human comprehension. This is the Boötes Void, a spherical region of space so desperately empty it has earned the nickname the Great Nothing. Its discovery in the early 1980s was not the result of seeing a dark spot in the sky, but of meticulously mapping the three-dimensional positions of galaxies. Astronomers Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman were conducting a large redshift survey, measuring how fast galaxies were moving away from us to determine their distances. As they pieced together their map of the universe, they stumbled upon a gaping hole in the constellation of Boötes, a place where the expected tapestry of galaxies simply vanished. To truly grasp the scale of this void is to confront the sublime. It is approximately 330 million light-years across. To put that inconceivable distance into perspective, if you could travel at the speed of light, it would take you over 300 million years to go from one side to the other. Our entire local group of galaxies, which includes Andromeda and the Milky Way, is just a fraction over 10 million light-years wide. You could fit our entire local universe and thousands of others into this one sphere of near-nothingness. When it was first found, only a single, lonely galaxy was known to reside within its immense volume. Subsequent deeper surveys have found a few dozen more, but that number is still shockingly small. In a region of space that should contain thousands of bright galaxies based on the average density of the universe, there are perhaps only 60. This makes the Boötes Void one of the emptiest places we have ever identified. The existence of such a colossal void presents a fascinating puzzle for cosmologists. How does the universe, in its grand structuring, create a bubble of this magnitude? The answer is woven into the very fabric of the cosmos, a concept known as the cosmic web. This is the idea that the universe is not a uniform soup of galaxies, but is instead structured like a sponge or a net, with long, dense filaments of dark matter and galaxies surrounding vast, empty voids. This web is the result of the subtle influence of dark matter and the relentless pull of gravity over billions of years. Tiny, random fluctuations in the density of the primordial universe, imprinted just after the Big Bang, were amplified by gravity. Slightly denser regions attracted more and more matter, growing into the walls and filaments, while the less dense regions were left behind, expanding and emptying out as the universe stretched. The Boötes Void is one of these underdense regions, a bubble that lost the cosmic lottery and was left behind in the race to gather matter. Computer simulations of the universe's evolution are crucial to understanding this process. When scientists run models based on our standard cosmological parameters, they do indeed see vast voids forming, but a void as large as the one in Boötes sits right on the edge of what these models predict is probable. Its existence challenges our understanding of just how extreme the universe's structure can become. One compelling theory for its formation suggests it might be the result of smaller voids merging over time. Imagine several smaller bubbles of emptiness forming close to each other in the early universe. As space expands, these bubbles could have grown and eventually merged into one gigantic supervoid. Another, more speculative idea involves the influence of quintessence, a dynamic form of dark energy whose repulsive force could have actively pushed matter out of the region, sculpting the void through a more active process than simple gravitational neglect. For the few galaxies that do call this void home, life is incredibly isolated. These void galaxies are fascinating objects in their own right, evolving in near-total isolation for billions of years, largely free from the gravitational harassment and galactic mergers that are common in denser clusters. They offer astronomers a unique laboratory. Studies suggest that void galaxies can be older, more pristine, and slower to evolve, preserving a record of what galaxies looked like in the early, quieter universe. Their very existence within the void tells us that even the deepest deserts of space are not completely barren. A few hardy islands of matter manage to form against all odds. The Boötes Void stands as a monument to the universe's overwhelming emptiness, a stark reminder that the glittering tapestry of galaxies we so admire is merely the bright embroidery on an immeasurably large and mostly dark cosmic canvas. But as we ponder the profound emptiness of the Boötes Void, we are reminded that what we cannot see often holds the greatest sway over the cosmos. This leads us to a different kind of mystery, one not defined by an absence of galaxies, but by the absence of light within a galaxy itself. Imagine a galaxy that spins just like our Milky Way with the same overall mass and structure, but when you point the most powerful telescopes at it, you see almost nothing. No grand spiral arms, no brilliant bulge of stars, just a faint, ghostly smudge. This is the enigmatic concept of a dark galaxy, a structure made almost entirely of dark matter, and one of the most compelling candidates for this bizarre object is known as Dragonfly 44. Discovered in the Coma Cluster, a dense gathering of galaxies over 300 million light-years away, Dragonfly 44 was first spotted by the Dragonfly Telephoto Array, a unique telescope designed specifically to detect extremely faint, diffuse light that conventional instruments miss. To the eye, it is utterly unremarkable, a faint, fuzzy blob that could easily be mistaken for a flaw in the image, but its mundane appearance hides an earth-shattering secret. When astronomers measured the motions of the few stars and globular clusters within it, they found they were zipping around at astonishing speeds. The laws of physics dictated that for these objects to be moving so fast without flying apart, the galaxy had to be held together by a tremendous amount of gravity. The calculated mass was enormous, on par with our own Milky Way. Yet, when they added up all the visible mass from its paltry collection of stars, it accounted for less than 1% of the total. The only explanation was that over 99% of Dragonfly 44's mass had to be in the form of dark matter. Confirming the nature of such an object is one of the most delicate challenges in modern astronomy. You cannot see or directly measure dark matter. You can only infer its presence by its gravitational influence on the things you can see. For Dragonfly 44, this meant using the Keck Observatory to take long-exposure spectroscopic measurements of its few dozen globular clusters. By carefully analyzing the subtle shifts in their light, astronomers could calculate their velocity and from that map out the mass distribution of the entire galaxy. The resulting graph is a stunning piece of evidence, a curve showing that the rotational velocity of the clusters remains high and flat all the way to the galaxy's outer edges. In a typical galaxy, this velocity should drop off as you move away from the mass concentration in the center. The fact that it doesn't is the classic signature of a massive, invisible dark matter halo exerting its overwhelming gravitational pull. The existence of such an object forces us to ask a fundamental question. How does a galaxy end up with almost no stars? One prevailing theory suggests that Dragonfly 44 is a failed galaxy. In the early universe, vast clouds of dark matter began to collapse, pulling in normal gas with them. In most cases, this gas would cool, condense, and eventually form stars. But in this specific case, something went wrong. Perhaps the gas was stripped away by the gravitational tides of other galaxies in the dense Coma cluster before it could form many stars. Or maybe the gas was simply too hot to condense effectively, or the process of star formation was somehow suppressed. What remains is the dark matter skeleton of a galaxy, a cosmic ghost that never quite woke up. However, not all astronomers are convinced. Some alternative explanations propose that Dragonfly 44 might not be a unique class of object, but rather the result of a more common process. It could be a large but fairly ordinary, ultra-diffuse galaxy whose population of stars has been tragically diminished over time through interactions with its violent cluster environment. Or the measurements of its mass could be off, influenced by the complex gravitational field of the entire cluster it resides in. The debate is far from settled, and it highlights the immense difficulty of studying the invisible majority of our universe. Each new observation, each deeper image from the James Webb Space Telescope, brings us closer to understanding whether Dragonfly 44 is a solitary freak of nature or a signpost pointing toward an entire hidden population of dark galaxies, a shadow universe of massive structures that have been hiding in plain sight all along. Moving from the profound emptiness of intergalactic voids and the ghostly nature of dark galaxies, we now turn our attention back to the vibrant, chaotic heart of our own Milky Way, where a different kind of invisible energy paints a mysterious picture. At the very center of our galaxy, astronomers have detected a brilliant, unexplained glow of high-energy gamma-ray light, a phenomenon that defies easy explanation and has sparked one of the most heated debates in modern astrophysics. This is the galactic center GVXS, a mysterious surplus of radiation that seems to emanate from the region around Sagittarius, a star, and its true source remains one of the most compelling whodunits in astronomy. The discovery of this excess is a story of patient data collection and powerful technology. It was the Fermi Large Area Telescope, or LAT, an instrument designed to scan the entire sky for gamma rays, that first revealed the anomaly. Scientists built intricate models of what the gamma-ray sky should look like, accounting for all known sources. The diffuse glow from cosmic rays interacting with interstellar gas, the distinct points of light from distant pulsars and active galaxies, and the structured bands of emission from the Milky Way's disk. But when they subtracted this model from the actual data Fermi collected, something remarkable was left over: a roughly spherical, diffuse glow of gamma rays, concentrated at the galactic center and shining with an energy of around 2 giga-electronvolts or GeV. It was an unexpected and persistent signal that refused to go away. This specific energy signature is the first major clue in the investigation. The gamma rays in the excess are not the highest energy photons Fermi detects, but they fall into a very specific and telling range. This mattered because the energy of a gamma-ray photon is like a fingerprint. It can tell us about the process that created it. The 2.5 GeV energy of these photons is precisely what many leading theoretical models predicted would be produced if two dark matter particles were to collide and annihilate one another. This immediately set off a wave of excitement. Could this be it? After decades of searching, had we finally found the first direct, observable evidence of dark matter, the invisible stuff that makes up most of the mass in the universe? The dark matter annihilation theory is an elegant and compelling solution. The idea is that our galaxy is embedded within a vast spherical halo of dark matter particles. According to the models, the density of this dark matter should be highest at the very center of the galaxy. If certain types of dark matter particles, known as weakly interacting massive particles or WIMP, exist, they could occasionally collide. And when they do, according to Einstein's famous equation E equals mc squared, their mass would be converted into a burst of pure energy, manifesting as a shower of particles and radiation, including gamma rays at that characteristic 2.5 GeV energy. The Fermi excess, with its spherical shape matching the predicted dark matter distribution and its perfect energy signature, seemed to fit the bill almost too well. It was a potential smoking gun for one of the universe's greatest mysteries. But in science, extraordinary claims require extraordinary evidence, and a competing theory soon emerged that offered a more conventional yet still fascinating explanation. What if the glow wasn't from annihilating dark matter, but from a vast population of incredibly dense, spinning stellar corpses that we simply hadn't seen yet? This is the millisecond pulsar hypothesis. Millisecond pulsars are neutron stars that have been spun up to incredible speeds by siphoning material from a companion star. They rotate hundreds of times per second, sweeping powerful beams of radiation across space like cosmic lighthouses. While individually bright, a large population of them could blend together into a diffuse, unresolved glow in Fermi's data. This theory gained significant traction when astronomers pointed other telescopes toward the galactic center. Using the Mercator radio array in South Africa, researchers went looking for the faint radio whispers that would be the telltale signature of individual pulsars. And they began to find them. Dozens of new millisecond pulsar candidates were discovered in the very region of the excess. Proponents of this theory argue that the galactic center, the most crowded stellar neighborhood imaginable, is the perfect environment to form legions of these objects through stellar interactions and binary mergers. They suggest that the excess isn't a smooth glow at all, but will eventually be resolved into thousands of individual points of light as our telescopes become more powerful. The debate between these two camps is a beautiful example of the scientific process at work. Each side scrutinizes the other's evidence. Proponents of the dark matter interpretation point out that the distribution of the gamma-ray signal is almost perfectly smooth, which doesn't quite match the clumpiness you'd expect from a population of distinct point sources. They also note that similar excesses have been found emanating from smaller dwarf galaxies orbiting the Milky Way, which are also thought to be rich in dark matter but are too faint to host a significant population of pulsars. On the other side, the pulsar advocates counter that our models for the background gamma-ray glow could be imperfect, and that we may be underestimating just how many stellar sources could be hiding in the galactic center's overwhelming glare. The truth may lie somewhere in the middle, or it may require a third, yet unthought of explanation. The hunt for the source of the galactic center excess continues to drive technological innovation, pushing the limits of our telescopes and our computer models. It has forced us to better understand the complex environment of our galaxy's core and to refine our theories about the fundamental nature of dark matter. This mysterious glow is more than just an astronomical curiosity. It is a cosmic crossroads where particle physics meets astrophysics, a puzzle whose solution could either reveal the identity of the universe's dominant material or uncover an entirely new understanding of the frenetic, star-packed chaos at the heart of every galaxy. After the intense mysteries surrounding dark matter and gamma rays, we turn our focus to an object that captivates not with its hidden power, but with its breathtaking and almost artificial beauty. In the constellation Monoceros, the unicorn, lies a nebula so geometrically perfect it seems to defy the natural chaos of the cosmos. This is the Red Rectangle Nebula, a celestial structure that appears less like a cosmic cloud and more like a piece of divine stained glass or a ladder being meticulously woven into the fabric of space itself. Its discovery story begins not with a visual observation, but with an infrared sky survey in the 1970s. Astronomers were using instruments designed to detect the heat signatures of celestial objects when they stumbled upon an incredibly bright infrared source. When they finally pointed optical telescopes toward these coordinates, they were met with a sight that was utterly unique. Instead of the amorphous, billowing clouds typical of planetary nebulae, they saw a distinct rectangular shape glowing with a deep, rich crimson hue. At its heart shone a bright central star, but further study revealed this was not a single star, but a close binary system, two stars locked in a tight orbital dance. This pairing, it turns out, is the master architect behind the entire spectacle. The true, jaw-dropping detail of the red rectangle's structure wasn't fully revealed until the Hubble Space Telescope turned its sharp eye toward it. Hubble's high-resolution imagery showed that the rectangle is actually an illusion, a trick of perspective. We are looking at two opposing cones of gas ejected from the central stars, and we happen to be viewing them almost directly from the side. This makes the rims of the cones appear to form the long edges of an X shape, which our brains then interpret as a rectangle. But the most astonishing feature, the one that truly sets this nebula apart, are the delicate, evenly spaced rungs that run horizontally across the cones, giving the entire structure the uncanny appearance of a celestial ladder or a spider's web. So how does a binary star system create such a precisely sculpted work of art? The process is a fascinating interplay of gravity, rotation, and stellar death. The central binary system consists of a dying red giant star and a smaller, denser white dwarf companion. As the red giant nears the end of its life, it puffs off its outer layers into space. However, the gravitational influence of its orbiting companion prevents this gas from expanding outward in a simple, spherical shell. Instead, the material is funneled into two opposing jets, shooting out from the poles of the system and forming the twin cones we see. The breathtaking rungs are thought to be the result of a periodic process. The outflow of gas isn't a smooth, constant stream, but happens in fits and starts. Every time the two stars in the binary system complete an orbit and reach their closest point, their gravitational interaction squeezes and ejects a new pulse of material from the red giant. This creates a series of expanding gas shells like rings of smoke from a pipe, all stacked within the conical outflow. Because the binary system's orbit is incredibly stable and regular, these ejections happen at precise intervals, creating those remarkably even spacings. Over time, as we view these concentric shells from the side, they appear as the distinct rungs of the cosmic ladder. The intense red color, which gives the nebula its name, comes from a specific type of carbon-rich molecule known as polycyclic aromatic hydrocarbons, or PAH. These complex organic molecules fluoresce, meaning they absorb invisible ultraviolet light from the hot central stars and re-emit it as a deep, ruby red glow. The presence of these molecules is another clue pointing to the advanced age and composition of the dying red giant, which has been busily manufacturing carbon in its core and now scattering it into the surrounding nebula. The red rectangle is therefore not just a marvel of geometry, it is also a vast chemical factory, seeding the interstellar medium with the complex building blocks of life. It stands as a stunning example of how the simple, repetitive laws of physics, acting over immense timescales, can produce structures of such intricate and seemingly impossible beauty. But for all its precise and patient artistry, the cosmos is equally capable of breathtaking violence, a fact perfectly embodied by our next strange object. If the red rectangle represents a careful, binary waltz, then the Black Widow pulsar is the ultimate cosmic predator, a celestial vampire slowly consuming its partner under the glare of its own lethal radiation. Discovered in the constellation Sagittarius, this system is not a serene painting but a horror story unfolding in the void, and it gets its chilling name from the female Black Widow spider, known for devouring its mate after reproduction. At the heart of this system lies a pulsar designated PSRB 1957+20. Like all pulsars, it is the rapidly spinning, ultra-dense corpse of a massive star that went supernova. This particular remnant spins hundreds of times per second, making it a millisecond pulsar. But its rapid spin is not its most fearsome feature. That title belongs to the incredible blast of energy it emits. The pulsar generates a fierce wind of high-energy particles and intense radiation that screams outward at nearly the speed of light, a perpetual hurricane of destruction. And orbiting perilously close to this maelstrom is a small, doomed companion star, locked in a gravitational embrace that will ultimately prove fatal. The dynamics of this relationship are both terrifying and fascinating. The two objects are locked in an incredibly tight orbit, completing a full revolution around each other in just over 9 Earth hours. The companion star is so close that it is tidally locked, meaning the same hemisphere forever faces the pulsar, just as our moon always shows the same face to Earth. This sets the stage for a gruesome one-sided assault. The pulsar's relentless particle wind and gamma-ray radiation blast the facing side of the companion star with the energy of a perpetual stellar explosion. This intense heating, focused on a single point, strips material away from the star's atmosphere, literally boiling it off into space. Astronomers can actually observe this process using a combination of radio and X-ray telescopes. Radio observations track the precise, clockwork pulses of the neutron star itself, while X-ray images reveal the glowing, superheated gas being torn from the companion, a shimmering plume of stellar material being siphoned away. The fate of the companion star is as grim as the system's name implies. It is being slowly, methodically evaporated. With each orbit, another layer of its being is scoured away by the pulsar's wrath. Estimates suggest this stellar victim has already been whittled down to less than 10 times the mass of Jupiter, a mere fraction of what it once was, classifying it as a brown dwarf or even a superplanet. It is a shadow of its former self, and the end of its story is written in the laws of physics. The pulsar will continue to feed, spinning ever faster as it accretes stolen mass and angular momentum, until eventually the companion star is completely dissolved. All that will remain is an isolated, rapidly spinning millisecond pulsar, a silent tombstone for the companion it utterly annihilated. The discovery and study of Black Widow systems and their relatives, the redbacks, which have slightly larger companions, are about more than just cataloging cosmic violence. They are crucial laboratories for understanding extreme physics. They show us how millisecond pulsars are recycled, spun up to incredible speeds by accreting matter from a donor star. They allow us to study the behavior of matter and intense magnetic fields in environments we could never hope to recreate. And perhaps most intriguingly, they might even help us in the hunt for dark matter. Some theories suggest that the dense cores of these evaporated companions could be made of exotic, dense forms of matter, or that the particles flying off the pulsar could themselves be interacting with dark matter in detectable ways. The Black Widow pulsar is a stark reminder that the universe operates on a scale of both sublime beauty and terrifying ferocity, where the laws of physics can write tales of creation and destruction with equal, indifferent power. Yet for all the precision of its celestial clock and the lethality of its radiation, the universe is also a master of coincidence, where chance alignments in the sky can create illusions that both delight and confound us. One of the most charming examples of this sits in the constellation Sagittarius, where a simple pattern of stars has been imagined by stargazers for centuries as a teapot. The handle, lid, and spout are all there, sketched out against the bright backdrop of the Milky Way center. It's a familiar, friendly sight for amateur astronomers. But pointing directly away from the tip of that teapot spout, as if steam billowing into the cosmos, is one of the most powerful and mysterious sources of gamma-ray radiation in our entire galaxy, an object known to science as HESS J1640465. This source wasn't discovered by looking through an eyepiece. It was found by sensing the universe's most violent light. The High-Energy Stereoscopic System, or HESS, is an array of telescopes in Namibia specifically designed to detect gamma rays not directly, but by the faint, fleeting flashes of blue light they create when they strike Earth's upper atmosphere. Scanning this region of the sky, the HESS array revealed an incredibly bright, hard-to-miss beacon of high-energy radiation. The problem wasn't finding it, it was figuring out what exactly was producing it. The gamma-ray emission is like a brilliant spotlight shining from behind a thick curtain. We can see the light clearly, but the object casting it remains frustratingly hidden from view. The primary suspect for generating such intense energy is a pulsar wind nebula. Think of this as the aftermath of a supernova explosion, a cosmic engine powered by the corpse of a massive star. When a star goes supernova, its core can collapse into a rapidly spinning neutron star, a pulsar. This city-sized object possesses a magnetic field, SO Chinese letter. It can tear apart atoms and accelerate particles to nearly the speed of light. The pulsar generates a fierce wind of these energetic particles, which then plows into the expanding shell of gas from the original supernova explosion. This collision creates a vast, glowing cloud of radiation that shines brightest in high-energy light like X-rays and gamma rays. HESS J1640465 has all the hallmarks of such an object. It's incredibly luminous in gamma rays and has a distinct, extended structure that suggests a cloud of energetic particles, not just a single point source. However, confirming this theory has proven to be a monumental challenge. The central region of our galaxy is the most crowded and obscured place we can observe, packed with stars, gas, dust, and other supernova remnants. Peering into this chaos to find the single pulsar that must be powering the nebula is like trying to spot a specific flashlight in a dense fog during a fireworks display. Astronomers have searched for the telltale blink of a rotating neutron star in radio waves and X-rays, but so far, the central engine has eluded detection. It might be that the pulsar is simply too faint, or its beam of radio waves isn't pointed toward Earth. Alternatively, the dense material between us and the galactic center could be blocking our view, preventing the faint pulses from ever reaching our telescopes. This is where the power of multi-wavelength astronomy comes into play. To solve the puzzle, scientists don't rely on a single type of light, they combine them all. They create overlays, stacking images from gamma-ray telescopes like HESS, X-ray observatories like Chandra, and infrared telescopes like Spitzer that can see through the dust. The resulting composite image is a masterpiece of cosmic detective work. The gamma-ray emission from HESS appears as a large, smooth cloud, defining the extent of the pulsar wind nebula. Within that cloud, X-ray data might reveal a smaller, brighter knot of emission, the probable location of the hidden pulsar itself, where the particle wind is most intense. And all of this is set against the infrared backdrop of the swirling dust and gas that fills the region, the very material that makes the search so difficult. This layered approach is our best tool for mapping the invisible and understanding the furious energy that lies behind the simple, serene shape of the teapot in the night sky. But the universe is not always a place of serene artistry or predictable orbits. Sometimes it delivers a spectacle of pure, unbridled chaos. Imagine a supermassive black hole, an object with the mass of 20 million suns, a gravitational anchor that should sit firmly at the heart of its galaxy. Now imagine that anchor torn loose and sent careening through the void at speeds of over 5 million miles per hour, a runaway behemoth leaving a breathtaking trail of newborn stars in its wake. This is not science fiction. It is the incredible story hinted at by observations from the Hubble Space Telescope, a discovery that challenges our very understanding of how black holes interact with their homes. The first clue was a long, almost perfectly straight line of light. Astronomers were studying a compact galaxy named RC F208258 when they noticed a brilliant linear feature stretching away from its core. At the tip of this cosmic brushstroke was a bright, compact source of light. Initial interpretations suggested it might be an imaging artifact, a scratch on the digital sensor, or perhaps a rare type of gravitational lensing effect. But follow-up spectroscopic observations revealed something far more astonishing. The linear streak wasn't a flaw or an illusion. It was a trail of intensely blue young stars, and the point of light at its tip was a quasar, a brilliantly shining supermassive black hole. The conclusion was as shocking as it was simple. The black hole had been ejected from its host galaxy and was now blazing a path through intergalactic space, and the tremendous forces of its passage were triggering star formation along a narrow corridor behind it. The immediate and pressing question is, how do you kick a black hole weighing 20 million suns out of a galaxy? The force required is almost beyond imagination. The leading theory points to one of the most violent events in the universe, the merger of two supermassive black holes. When two galaxies collide, their central black holes will eventually sink to the new common center through a process called dynamical friction. They form a binary pair, orbiting each other ever closer until they finally merge. According to Einstein's theory of general relativity, such a merger doesn't happen quietly. It is the most energetic event since the Big Bang, releasing a stupendous amount of energy in the form of gravitational waves, ripples in the fabric of space-time itself. This is where the physics gets truly fascinating. Gravitational waves aren't just emitted equally in all directions. If the two black holes have unequal masses or their spins are misaligned with their orbital plane, the waves can be shot out more powerfully in one direction. To conserve momentum, the newly merged black hole must recoil in the opposite direction, like a rocket firing its engine. In most cases, the kick isn't strong enough to overcome the immense gravitational pull of the galaxy's core. But in rare instances, with just the right combination of mass and spin, the recoil could be powerful enough to eject the newborn supermassive black hole entirely, sending it racing out into the void. This phenomenon, known as gravitational wave recoil, had long been predicted by theorists, but the Hubble observation provides what may be the first tangible evidence of it occurring in nature. The stunning trail of young stars is the corroborating evidence that makes this case so compelling. As the black hole plows through the dense clouds of gas that surround its host galaxy, it doesn't just move through them, it interacts violently. The immense speed and gravitational shock of its passage compress the gas in its wake. Think of a ship plowing through the ocean, creating a wake of churned water behind it. In this case, the water is interstellar hydrogen gas, and the churning is so extreme that it triggers gravitational collapse. the gas clouds become dense enough and cool quickly enough to ignite a frenzy of star formation, leaving behind a linear nursery of brilliant new suns that mark the black hole's escape route like a dotted line on a map. Of course, such an extraordinary claim faces healthy scientific scrutiny. Some alternative explanations propose that the linear feature might be a jet of material powered by the black hole itself, though its remarkable straightness and the lack of associated radio emission make this less likely. Others suggest we might be seeing a rare edge on galactic disk. However, the sheer intensity of the star formation and the precise alignment with the displaced quasar make the runaway black hole hypothesis the most captivating and plausible scenario. This object stands as a potential Rosetta Stone for astrophysicists, a real-world example of the extreme dynamics that can occur during galaxy mergers and the dramatic, universe-shaping power of gravitational waves. It shows us that even the most massive objects are not immune to the violent currents of the cosmos, and that sometimes the universe itself can fire a bullet of pure gravity across the vast expanses of space. From the chaos of a runaway black hole carving a trail of starlight, we now shift our focus to a discovery born not from the sheer violence of the cosmos, but from the collective curiosity of hundreds of thousands of volunteers. This story brings us to a class of objects so small and seemingly insignificant that they were overlooked by professional astronomers for years, hiding in plain sight within a massive digital sky survey. They are known as the green pea galaxies, and their unassuming name belies their profound importance as windows into the universe's explosive infancy. Their origin story is a testament to the power of public participation in science. The Sloan Digital Sky Survey, one of the most ambitious astronomical projects ever undertaken, had imaged and collected spectra for millions of galaxies. With such a colossal dataset, researchers faced a monumental task: how to classify everything. The solution was the Galaxy Zoo project, which invited ordinary people around the world to log on and help categorize galaxy shapes. It was within this vast digital catalog that volunteers began noticing something unusual. Among the spirals and ellipticals were tiny, round, and unmistakably green objects. They were so distinct that users on the project's forum started calling them green peas. The name stuck, and a new class of galaxy was officially recognized, discovered not by a PhD, but by the keen eyes of citizen scientists. But what exactly are these green peas? Each one is a relatively small, compact galaxy, but don't let their size fool you. They are anything but quiet. These galaxies are undergoing an absolutely ferocious burst of star formation. While our own Milky Way might form 1 or 2 new stars per year, a green pea galaxy, which might be 10 times smaller, can be producing new stars at a rate 10 times faster. This incredible energy output is the key to their peculiar color. The intense ultraviolet light from all these hot, newborn stars is flooding the galaxy, exciting the surrounding clouds of gas. This process causes specific elements within the gas to fluoresce, much like the gas in a neon sign. In the case of the peas, the strongest emission comes from doubly ionized oxygen, which glows with a very specific shade of green. This light is so dominant that it overpowers all other colors from the galaxy, giving these objects their distinctive, almost electric green hue in the Sloan Digital Sky Survey images. This unique property makes them incredible analogs for the first galaxies that ignited in the early universe. After the Big Bang, the universe was a dark, opaque fog of neutral hydrogen gas. The first stars and galaxies had to literally blow away this fog, a process known as cosmic reionization, by flooding the cosmos with the same kind of energetic ultraviolet light that the green peas produce today. For astronomers, finding a modern-day example of such a process is like discovering a living dinosaur. The peas offer a nearby laboratory to study the mechanics of how intense starlight can escape a galaxy and interact with the surrounding intergalactic medium. By studying the spectra of these green galaxies, scientists can see the clear signatures of these leaky galaxies, with evidence that a significant portion of their energetic light is indeed punching out into space, just as it did billions of years ago to clear the cosmic dawn. Their significance is even greater than just being a local proxy. Detailed analysis suggests that green P galaxies are exceptionally rich in heavy elements, yet they are also incredibly primitive in their composition. They possess a high abundance of oxygen and nitrogen relative to hydrogen, but they lack the dust and complex chemistry of older, more evolved galaxies. This places them in a special transitional phase, offering a snapshot of a galaxy's chemical evolution that is crucial for understanding how the early universe became seeded with the elements necessary for planets and life. They are not the first galaxies, but they behave like them, providing a unique and accessible link to an era that is otherwise incredibly difficult to observe directly. In these small, green, and fiercely energetic objects, we have found a vital piece of the puzzle, showing us how the universe transformed itself from a dark, simple sea of gas into the brilliant, complex cosmos we see today. Leaving behind the brilliant, star-forming fury of the green peas, we venture into a controversy that strikes at the very heart of our place in the cosmos, a debate over the identity of a vast structure that may either be our closest galactic neighbor or a spectacular illusion. This is the mystery of the Canis Major overdensity, a colossal swarm of stars discovered not by seeing a new shape in the sky, but by counting millions of points of light and noticing a pattern that shouldn't be there. The story of its discovery is a tale of modern, data-driven astronomy. In the early 2000s, astronomers were analyzing the first massive stellar surveys, particularly the 2-micron all-sky survey, or 2MASS, which mapped the entire sky in infrared light. This wavelength is crucial because it allows us to peer through the obscuring curtains of dust that fill the plane of the Milky Way. As researchers sifted through the data, meticulously counting and mapping the red giant stars' bright, elderly stars that make excellent distance markers, they noticed an astonishing concentration. A huge, rich overdensity of these stars was located in the constellation Canis Major, the Great Dog, seemingly just a stone's throw from our solar system in galactic terms, a mere 25,000 light-years from Earth and well within the confines of our own galaxy's halo. This was no minor clustering. The structure appeared to be the core of a dwarf galaxy, a system that, if confirmed, would be the closest satellite galaxy to the Milky Way, even closer than the long-accepted Sagittarius dwarf elliptical galaxy. The evidence seemed compelling. The stars in this overdensity weren't just clustered together. They were moving as a coherent group, sharing a common velocity distinct from the general motion of the Milky Way stars, a classic signature of a gravitationally bound system. Furthermore, the population of stars within it was distinctly different from those in the galactic disk, containing a high number of ancient, metal-poor stars, which is exactly what astronomers expect to find in a small, primordial dwarf galaxy that formed early in the universe's history. This led the discoverers to a dramatic conclusion. We were witnessing the final act of a cosmic consumption, the ongoing cannibalization of the Canis Major dwarf galaxy by our own Milky Way, its stars being torn away by tidal forces to form great streams that would eventually merge entirely with our galactic halo. However, extraordinary claims in science inevitably attract intense scrutiny, and the galactic cannibalism hypothesis soon faced a powerful and persuasive counter-argument. A different group of astronomers proposed that this vast collection of stars might not be an invading galaxy at all, but rather a part of our own Milky Way that we had simply failed to understand. This alternative theory centers on the concept of the galactic warp. Our galaxy's disk, like many others, is not a perfectly flat plane. The immense gravitational influence of the surrounding dark matter halo and the tug of satellite galaxies like the Large and Small Magellanic Clouds can cause the entire disk to bend and warp, much like a vinyl record left in the sun. From our vantage point embedded deep within this warped disk, certain perspectives can create profound illusions. The skeptics argued that the Canis major overdensity is precisely this kind of illusion, a perspective effect. They suggest we are looking directly down a spiral arm, specifically the norma or outer arm, that is itself severely warped. This warp brings a huge section of the arm much closer to us than standard models had predicted, and it also bunches the stars within it closer together from our point of view. When we count the stars in that direction, we're not seeing the core of a separate galaxy. We're simply seeing a denser, nearer section of our own galaxy's distorted spiral structure. The common motion of the stars is not evidence of a separate entity, but simply the shared orbital dynamics of stars within that particular warped segment of the disk. This interpretation turns a dramatic story of galactic conquest into a more nuanced tale of galactic architecture and our own limited viewpoint. The debate between these two camps is far from settled, and it is fought with the most advanced tools of astronomy. The key evidence comes from panoramic maps of the Milky Way, like those created by the Gaia spacecraft. Gaia's precise measurements of stellar distances and motions allow scientists to construct stunning three-dimensional maps of our galaxy's structure. When they plot the positions of the stars attributed to the Canis major overdensity, they don't see a neat, spherical cloud typical of a dwarf galaxy's core. Instead, many argue the data reveals an elongated, arc-like structure that closely follows the expected line of the warped outer disk. Stellar density plots become the battleground, with each side interpreting the subtle contours and gradients in the data to support their case. Ultimately, the Canis major overdensity remains one of the most significant and intriguing puzzles in modern galactic astronomy. It forces us to acknowledge the immense difficulty of mapping our own galaxy from a position inside it, where perspective and occlusion can create phantoms and hide giants. Whether it is a doomed galaxy in its final death throes or a magnificent ripple in the fabric of our own Milky Way, its discovery has profoundly sharpened our tools and our theories, pushing us to see the familiar stars of our night sky not as a fixed tapestry, but as a dynamic and three-dimensional structure whose full shape we are still struggling to comprehend. Yet even as we map the grand, warped architecture of our own galaxy, we occasionally catch a glimpse of a structure so perfectly formed it seems almost too ideal to be real. Far beyond the Milky Way's halo, in the vast expanse of intergalactic space, lies a celestial marvel that looks less like a naturally occurring galaxy and more like a brilliant piece of cosmic jewelry. This is Hoag's object, a galaxy that has become the iconic example of a ring galaxy, a stunningly symmetrical circle of young, blue stars surrounding a core of ancient yellow stars, with a seemingly empty, dark gap separating the two. It is so geometrically perfect it appears artificial, a giant's diamond ring cast adrift in the void. And while no such perfect ring exists within our own galaxy, the Milky Way's vicinity holds its own mesmerizing examples of these rare, enigmatic structures, challenging our understanding of how galaxies evolve and maintain such breathtaking order. The story of Hoag's object's discovery is a classic tale of serendipity in astronomy. In 1950, astronomer Art Hoag was surveying the sky for planetary nebulae when he stumbled upon this bizarre, ring-like object in the constellation Serpens. Unsure of what he was seeing, he even entertained the possibility that it was a gravitational lensing effect, a trick of light. But further observations confirmed its true nature, a galaxy unlike any other in the catalogues. Its unique structure presented an immediate and profound puzzle. How does a galaxy form with such a distinct separation between its core and its disk? The two most prominent theories both involve immense cosmic violence, a far cry from the serene beauty of the final product. The first and most widely accepted theory is that of a galactic collision. Imagine a smaller, compact galaxy shooting like a bullet through the center of a larger, disk-shaped galaxy. The gravitational shockwave from this direct hit would send ripples of density through the larger galaxy's disk, compressing gas and triggering a wave of star formation that propagates outward, ultimately creating that brilliant blue ring of newborn stars. The central core of the original galaxy would remain largely undisturbed, left sitting in the middle of this newly forged circle of light. The second theory suggests a process that is less about a dramatic accident and more about a fundamental instability. It's possible that in some galaxies, a central bar structure made of stars like the one in our own Milky Way could become unstable over billions of years. This instability might cause the bar to effectively break apart, with its stars migrating inward to puff up the core, while the gas in the outer disk collapses inward due to gravitational forces, only to rebound and create a propagating ring of star formation. While this avoids the need for a specific collision, it requires a very precise and delicate set of conditions to create a ring as perfectly symmetrical as Hoag's object. Regardless of the exact trigger, the result is a galaxy frozen in a single, magnificent moment of its evolution, a snapshot of a dynamic process that has temporarily created a form of perfect celestial balance. While we don't have a perfect twin of Hoag's object right next door, our local galactic neighborhood does offer fascinating examples of ring structures that help us understand the phenomenon. One of the most stunning is the Cartwheel Galaxy, located about 500 million light-years away. This galaxy provides what might be the clearest smoking gun evidence for the collision theory. Hubble Space Telescope images show it in incredible detail. A brilliant outer ring of intense star formation, a smaller inner ring, and a dusty, spoke-like structure connecting them to a slightly off-center core. The entire system looks like a wagon wheel spinning in space, and the reason is written in the galaxies around it. To the left of the cartwheel are two smaller galaxies. Spectroscopic evidence strongly suggests one of them recently plunged directly through the cartwheel's center. The ripples from this collision are still moving through the galaxy, a literal bullseye etched into the cosmos by a direct hit. Closer to home, within our own Milky Way sphere of influence, we find evidence that these processes can occur on a smaller scale. Some distant planetary nebulae, the glowing shells of gas ejected by dying sun-like stars, exhibit distinct ring shapes, though these are in no way related to galactic structure. More significantly, studies of the Andromeda Galaxy, our closest major galactic neighbor, have revealed faint, massive rings of stars in its halo. These are thought to be the fossilized remains of smaller galaxies that were cannibalized by Andromeda, their stars torn apart and stretched into vast circular streams that orbit the larger galaxy. While not the pristine star-forming rings of Hoag's object, these structures show that gravitational interactions can indeed create large-scale ring-like formations. The study of these rare ring galaxies is about more than just cataloging beautiful anomalies. They offer a unique laboratory for understanding star formation under extreme conditions. The compressed gas in the expanding ring of a galaxy like Hoag's object or the Cartwheel Galaxy creates an environment where stars are born in a coherent, massive wave. This allows astronomers to study an entire life cycle of stellar creation at once, from the initial collapse of gas clouds to the emergence of brilliant young star clusters and the eventual death of the most massive stars in supernova. By comparing these perfect rings to the more common and messy spiral galaxies like our own, we gain a deeper appreciation for the myriad ways gravity and motion can sculpt the universe, creating both the chaotic beauty of a spiral and the sublime, almost mathematical perfection of a ring. But for all the brilliant structures we can see, from the perfect ring of Hoag's object to the warped disk of our own Milky Way, they all share a profound and humbling secret. What we observe is only a tiny fraction of what is actually there. The stars, the gas, the dazzling nebulae, all of this luminous matter is merely the glittering decoration on an immense, invisible framework. This brings us to the most massive and mysterious object in our entire galactic neighborhood, one that envelops everything we've discussed so far, the dark matter halo of the Milky Way. It is the ultimate cosmic ghost, an unseen ocean of mass that dictates the motion of every star within our galaxy, yet it has never been directly seen or touched. The first compelling evidence for this invisible giant came not from deep space, but from the careful study of our own galactic backyard. For centuries, astronomers assumed that the Milky Way, like our solar system, was governed by gravity in a straightforward way. The vast majority of the mass, they reasoned, was concentrated in the bright central bulge and the disk of stars. According to Kepler's laws of motion, this meant that stars in the outer reaches of the galaxy, far from the central mass, should orbit much more slowly, just as Pluto moves more slowly around the Sun than Mercury does. But when astronomers like Vera Rubin and Kent Ford began measuring the rotational velocities of stars and gas clouds at different distances from the galactic center in the 1970s, they found something astonishing. The velocity of these outer objects didn't drop off as expected. Instead, the rotation curve, the graph plotting orbital speed against distance from the center, remained flat. Stars on the very fringes of the galaxy were whipping around just as fast as those closer in. This was a direct violation of the predictions based on visible matter alone. The only possible explanation was that there had to be a tremendous amount of additional mass that we could not see, providing the extra gravitational pull to keep those high speeds from flinging the stars off into intergalactic space. This invisible mass couldn't be concentrated in the center. To create a flat rotation curve, it had to be distributed in a vast spherical halo that extended far beyond the visible edge of the Milky Way. Imagine our galaxy not as a frisbee of stars, but as that same frisbee embedded in a gigantic, invisible beach ball of dark matter, a ball that contains over 10 times more mass than everything we can see combined. So what are the properties of this all-encompassing halo? Modern observations and sophisticated computer simulations have given us a surprisingly detailed profile of our invisible landlord. We believe the Milky Way's dark matter halo is roughly spherical, extending over 600,000 light-years from the center, more than twice the diameter of the visible stellar disk. Its density is thought to be highest at the core and gradually decreases as you move outward. We can map this distribution not only with rotation curves, but also by studying the motions of small satellite galaxies and even individual stars in the halo that act as tracers, their paths dictated by the gravitational tug of the unseen mass. Furthermore, the halo is not a perfect, smooth sphere. The lambda-CDM model of the universe predicts that it should have a certain amount of lumpiness or substructure, with smaller clumps of dark matter orbiting within the larger halo, the ghostly remnants of smaller galaxies that were absorbed long ago. The greatest mystery, of course, is what this halo is actually made of. We know what it's not. It's not planets, black holes, or clouds of normal gas made of protons and neutrons, as these would interact with light and reveal themselves. The leading theoretical candidate for decades has been a hypothetical particle known as a WIMP, or weakly interacting massive particle. These particles would be heavy, move relatively slowly, and as their name implies, interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. Dozens of ambitious experiments are buried deep underground in old mines and tunnels, shielded from cosmic rays, hoping to catch the exceedingly rare ping of a WIMP colliding with an atomic nucleus in a vat of ultra-pure xenon or germanium. So far, these direct detection experiments have yet to find a confirmed signal. Other creative methods are also being employed to hunt for dark matter. Astronomers use a phenomenon called gravitational lensing, an effect predicted by Einstein where the gravity of a massive object, like a clump of dark matter, warps the fabric of space-time, bending and magnifying the light from a more distant galaxy behind it. By studying these distorted cosmic mirages, we can literally map the distribution of the invisible mass causing the distortion. Another approach involves looking for indirect signals of dark matter annihilation. If two dark matter particles were to collide and annihilate each other, they might produce a shower of secondary particles we can detect, like gamma rays, neutrinos, or positrons. Telescopes like Fermi are constantly scanning the sky, particularly the dense center of our galaxy's halo, for any unexplained excess of this radiation that could be the signature of these elusive particles. The ongoing quest to identify the dark matter particle is one of the most fundamental challenges in all of physics. Its resolution will not only tell us what makes up most of our galaxy, but will also likely lead us to a new, deeper understanding of the universe itself, potentially revealing laws of physics that operate beyond our current standard model. The dark matter halo is the ultimate strange object. It is the architecture of our galaxy, the hidden hand that guides every orbit, the invisible ocean in which our island of stars floats. It is a constant reminder that the universe is dominated not by what shines, but by what silently holds the light together. For our entire journey so far, we've been pulled toward the brilliant, chaotic, and immensely crowded heart of the Milky Way. It's the place of greatest drama where supermassive black holes and stellar megastructures command our attention. But what happens if we do the exact opposite? What lies in the direction we're facing when we turn our backs on the galactic core? This brings us to one of the most conceptually fascinating regions in the entire sky, the galactic anticenter. It's the official point on the celestial sphere directly opposite the supermassive black hole in Sagittarius, a star located in the constellation Taurus, not far from the familiar star Aldebaran. While it might sound like a place of profound emptiness, the anticenter is anything but a boring void. In fact, it's an incredibly privileged viewpoint, a cosmic window that looks directly outward along the plane of our galaxy's disk. Because we are situated about 27,000 light-years from the center, looking toward the anticenter means we are gazing toward the very outer fringes of the Milky Way spiral structure and beyond into the intergalactic void. This unique sightline offers a far clearer view than we get toward the crowded, dust-choked center, allowing astronomers to study the precise architecture of our galactic disk and the faint, ghostly remnants of its ancient history. Some of the most compelling discoveries in this region come from the painstaking work of all-sky surveys, which have mapped the positions and motions of millions of stars. One of the strangest structures found is the anticenter stream, a vast, ribbon-like chain of stars arching across the sky. This isn't a spiral arm or a gas cloud, it's a tidal stream, the celestial equivalent of breadcrumbs left behind from a cosmic feast. The leading theory suggests this stream is the shredded remains of a much smaller dwarf galaxy that ventured too close to the Milky Way billions of years ago. Our galaxy's immense gravity tore it apart, stretching its stars into a long, elliptical orbit that we now see from a perfect side-on perspective, tracing a delicate path that seems to emanate from the anticenter itself. But the anticenter stream isn't the only ghost at this outer frontier. Surveys have also revealed other faint stellar groupings with names like the Triangulum Andromeda stream and the A13 overdensity. These are all likely the splintered remains of ancient globular clusters or even smaller galaxies that were cannibalized by the Milky Way, their stars now scattered and orbiting together as a faint testament to their shared origin. Studying these structures is like doing galactic archaeology. By tracing the motions and compositions of these stars, we can piece together the timing and violence of these long-ago mergers, helping us write the early history of our galaxy's growth. The anticenter is also a fantastic place to study the raw building materials of the galaxy. Without the blinding glare and thick dust of the inner galaxy, astronomers can get an unparalleled view of the outer galactic disk and the halo beyond. Vast, faint gas clouds, like the complex known as the anticenter high-velocity cloud, can be seen. These are massive reservoirs of neutral hydrogen, some of which may be pristine gas falling into the Milky Way for the very first time, ready to fuel future generations of star formation. Others might be material that was blasted out of the disk by ancient supernova explosions and is now raining back down. It's a dynamic region where the cycle of galactic ecology, the inflow of new gas and the recycling of old material is on full display, offering a clearer view of these processes than we could ever get from our vantage point closer to the downtown chaos. After contemplating the grand, invisible architecture of our galaxy's dark matter halo and the quiet frontier of the anticenter, we now turn to the most dynamic and rebellious members of our galactic family, stars that refuse to be bound by its gravitational rules. These are the hypervelocity stars, stellar projectiles rocketing through the Milky Way at such incredible speeds that they are destined for one outcome: a one-way ticket out into the limitless void of intergalactic space. They are the cosmic equivalent of a slingshot fired with such force that it escapes Earth's gravity, but on a scale so immense it defies belief. The existence of these stellar speedsters was purely theoretical until the early 2000s, when an astronomer named Warren Brown was meticulously studying spectra from the Sloan Digital Sky Survey. He was looking for distant, ancient stars in the galactic halo when he found something completely unexpected: a star moving toward us at a velocity of over 700 kilometers per second. That's more than 1.5 million miles per hour. Calculations showed this star wasn't just orbiting quickly, it was moving fast enough to completely overcome the gravitational pull of the entire Milky Way. The discovery sent a shockwave through the astronomical community, forcing everyone to ask a single, pressing question: what kind of cosmic catapult could possibly launch a star to such a phenomenal speed? The prime suspect for creating these extreme velocities is the supermassive black hole at our galaxy's center, Sagittarius, a star. The leading theory involves a tragic game of gravitational billiards played with 3 stars. Imagine a binary star system, 2 stars orbiting each other, wandering too close to the black hole's immense gravitational well. The black hole's tidal forces can violently disrupt this pair. In a process known as the Hill's mechanism, one star is captured into a tight orbit around the black hole, while its companion is flung away at an astonishing percentage of the speed of light. It's a cosmic slingshot where the black hole acts as the pivot point, transferring an enormous amount of orbital energy from the captured star to the ejected one, which then rockets out of the galactic core like a bullet from a rifle. Computer simulations of this 3-body interaction show it is more than capable of generating the velocities we observe, providing an elegant, if violent, explanation for many of these runaway stars. However, not every hypervelocity star can trace its origin to the galactic center. A second, equally dramatic factor for these objects is the aftermath of a thermonuclear supernova explosion in a tight binary star system. In this scenario, 2 stars are locked in a close orbit, with one a dense white dwarf and the other a main sequence star like our Sun. The white dwarf siphons material from its companion until it reaches a critical mass and explodes completely in a Type 1 supernova. This instantaneously obliterates the white dwarf, severing the gravitational bond that held the binary pair together. The surviving companion star, suddenly freed from its orbital tether, is flung outward with whatever velocity it had at the moment of the explosion. It's like swinging a ball on a string around your head and then suddenly letting go. The ball flies off in a straight line. This mechanism can easily impart enough velocity to send the surviving star on an escape trajectory from the galaxy, a lonely survivor of its partner's catastrophic death. Tracking the paths of these stars is a monumental feat of astronomical detective work. It requires measuring not just their speed toward or away from us, their radial velocity, but also their proper motion, their tiny, actual movement across the sky. Space telescopes like Gaia are indispensable for this, providing exquisitely precise measurements of a star's position over time. By combining this data with distance estimates, astronomers can reconstruct a star's full three-dimensional velocity vector and trace its path backwards across the galaxy. The most thrilling discoveries are when that path leads directly back to the galactic center, pointing to the black hole as the likely ejector. Other times, the path might originate from a known supernova remnant or a dense stellar cluster, providing crucial clues to its history. Animations of these trajectories are breathtaking, showing a single star's swift, straight-line journey against the slower, graceful swirl of the galaxy's spiral arms, a stark contrast between a rebel and the rule-abiding population. The study of hypervelocity stars extends far beyond just cataloging their incredible speed. They serve as unique probes of the Milky Way's structure, particularly its dark matter halo. As a hypervelocity star races out from the center, its path is subtly bent by the gravitational pull of all the mass it passes, both visible and dark. By carefully measuring any deviations from a perfectly straight escape trajectory, astronomers can actually map the distribution of dark matter along its flight path. Each star becomes a single data point in a grand experiment to weigh and measure the invisible component of our galaxy. Furthermore, their composition tells a story. Many are blue, hot, and massive young stars that were likely part of a binary system. But some are older, sun-like stars, and their ejection challenges our models, suggesting that even quieter, older stellar neighborhoods can be the source of incredible cosmic violence. These stellar fugitives are more than just astronomical curiosities. They are high-speed messengers, carrying with them information about the most extreme environments and events in the galaxy, from the violent heart of a black hole to the shattering power of a stellar explosion. Yet, as we consider the immense power required to launch stars from our galaxy, we are reminded that the Milky Way itself has been the source of even more titanic eruptions. Our journey now takes us back to the very center of the galaxy, to a pair of colossal, invisible structures that stand as the most dramatic evidence of its violent history. But this isn't the story of a single discovery. It's a tale of two telescopes, two different forms of light, and two sets of mysterious bubbles that together reveal a cataclysm of almost unimaginable scale. The first chapter of this story began with the Fermi Gamma-ray Space Telescope. As it scanned the sky, it revealed two massive lobes of gamma-ray light ballooning outward from the galactic center, one above and one below the plane of the Milky Way. These Fermi Bubbles, as they became known, are staggering in size, each extending an astonishing 25,000 light-years from the core. They are filled with superheated gas and energetic particles moving at nearly the speed of light, a testament to some tremendous release of energy from the region of the supermassive black hole. For nearly a decade, these structures represented the primary evidence of a past galactic explosion, a cryptic message written in the universe's most energetic language. Then, in 2020, the next chapter was written by a different eye in the sky, the E-Rosetta X-ray telescope. This instrument, designed to survey the entire sky in soft X-rays, revealed something even more breathtaking. It found its own set of bubbles, perfectly aligned with the galactic center but vastly larger than the Fermi structures. The E-Rosetta bubbles are true behemoths, extending roughly 45,000 light-years from the galactic plane, a total height of nearly 90,000 light-years, enough to encompass the entire visible Milky Way disk within them. Unlike the gamma-ray glow of the Fermi bubbles, the E-Rosetta structures emit lower-energy X-rays, a softer glow that suggests a different physical process and a different history. Finding two sets of bubbles, one nested within the other, immediately presented astronomers with a fascinating puzzle. Are we looking at two separate events or two parts of the same incredible outburst? The most compelling theory suggests a single, two-stage cataclysm. Imagine a tremendous explosion at the galactic center, perhaps a feeding frenzy from the supermassive black hole or a ferocious wave of star formation. This event would have launched a powerful shockwave, a spherical blast of energy that expanded outward at incredible speed. The leading edge of this shockwave, plowing through the thin gas of the galactic halo, would have heated it to millions of degrees, causing it to glow in X-rays. This is what we see as the vast outer shell of the Boötes bubbles. Meanwhile, within this expanding sphere, the black hole's intense activity would have also generated a relentless wind of ultra-relativistic particles. This wind, flowing along the path of least resistance out of the galaxy's poles, would have filled the interior of the expanding shockwave. The fierce interactions of these particles within the bubble are what generate the high-energy gamma rays detected by Fermi. In this model, the Fermi bubbles are not a separate structure, but the energetic heart of the larger Boötes phenomenon, the engine room inside the larger balloon. The energy required to inflate such structures is almost beyond comprehension. Calculations suggest that the event would have needed to release a staggering amount of energy, equivalent to the simultaneous explosion of perhaps 100,000 supernovae. This wasn't a brief flash in the pan. The outburst likely lasted for millions of years, a sustained eruption that fundamentally reshaped the galactic environment around us. This energy estimate is a crucial clue pointing to the possible culprit. A starburst event with a frantic wave of star formation and subsequent supernova explosions could potentially generate such a powerful isotropic wind. However, the precise symmetry and focused nature of the bubbles also strongly suggest the involvement of the supermassive black hole, whose jets can channel energy with incredible efficiency. The truth may lie in a combination of both, a perfect storm of nuclear and gravitational fury at the galaxy's core. The true power of modern astronomy is revealed when we combine these different views. Multi-wavelength composite images are the key to unlocking this mystery. By layering the Fermi gamma-ray data over the Boötes X-ray map, scientists create a stunning and informative picture. The result shows the larger, softer X-ray bubbles acting as a vast container, with the sharper, more intense gamma-ray structures sitting neatly within them, extending about halfway to the outer edge. This visual relationship strongly supports the idea of a connected origin, with a single energetic event creating both the expansive shockwave and the ongoing particle acceleration within it. This incredible discovery does more than just add two new entries to a catalogue of cosmic curiosities. It fundamentally changes our understanding of the Milky Way's recent history. We now know that our galaxy is not a quiet, stable place. Just a few million years ago, a blink of an eye on cosmic timescales, the center of our galaxy was a raging inferno, a powerhouse of activity that ejected enough energy to create the largest structure we have ever detected emanating from our home. The Fermi and Boötes bubbles are a permanent, if invisible, monument to this eruption, a fossilized record of the moment the Milky Way's heart roared with a violence that echoed through tens of thousands of light years. They serve as a humbling reminder that even our own familiar galactic home has a dormant temper, capable of awakening with a force that shapes the cosmos on a truly grand scale. But the story of these immense galaxy-spanning bubbles does not end with their discovery in gamma rays and X-rays. There is another chapter to this violent history, one written not in the flash of high-energy light, but in the steady, whispering glow of radio waves. These observations reveal the intricate mechanics of the explosion itself, the vast magnetized conduits through which energy and matter were channeled out of the galactic center. They are known as the galactic geysers, and they show us the very pathways the eruption took, painting a vivid picture of how the Milky Way's heart can blast its influence far into the halo. The first clear evidence for these structures came from one of the most powerful radio telescopes on Earth, the Green Bank Telescope in West Virginia, as part of a survey called Galactic. Radio astronomy allows us to detect the faint emission from neutral hydrogen gas, the most abundant element in the universe. By meticulously mapping the subtle shifts in this radio light, astronomers can not only locate this gas but also measure its velocity, determining whether it is moving toward us or away from us. When scientists pointed this incredible instrument toward the galactic center, they detected something extraordinary: two massive, balloon-like structures of hydrogen gas expanding outward from the core at tremendous speeds. These weren't the hot, energetic bubbles seen by Fermi and Rosetta, but rather the cooler, denser material that was likely swept up and carried along by the eruption's powerful shockwave. It was as if we were seeing the immense blast wave from a cosmic explosion frozen in time, its progress charted by the cold gas it was pushing ahead of it. Further observations with the world's largest radio interferometer, the Milky Way array in South Africa, revealed the geysers in even more stunning detail. Milky Way's exquisite resolution and sensitivity allowed it to trace not just the gas, but also the magnetic fields embedded within it. The data showed that these outflows are not simple, amorphous clouds. They are highly structured, filled with intricate filaments and tendrils that trace the lines of powerful magnetic fields. These fields act like cosmic containment vessels, shaping and directing the flow of the outflows, preventing them from dissipating too quickly into the halo. This magnetic scaffolding is a crucial piece of the puzzle. It explains how the geysers have maintained their coherent, elegant structure over millions of years, even as they expand into the near vacuum of intergalactic space. The sheer power of this event is best understood by looking at the numbers. The material within these geysers is not drifting lazily, it is being hurled outward with immense force. Measurements indicate the gas is moving at velocities exceeding 600 kilometers per second. To escape the gravitational pull of the entire Milky Way, an object needs to achieve a velocity of about 550 kilometers per second. This means the geysers are not just a flow, they are a galactic-scale fountain, actively pumping millions of solar masses of gas clear out of the galaxy's gravitational grasp. This process, known as galactic feedback, is a fundamental regulator of how galaxies evolve. By violently ejecting gas, the very fuel for future star formation, the central black hole or starburst event can effectively shut down its own future growth, a self-regulating mechanism that prevents galaxies from becoming too large. The connection between these radio geysers and the larger Fermi and Rosetta bubbles is a subject of intense study, and the evidence points toward a single, unified cataclysm. The most widely accepted model suggests a multi-stage event. It began with a colossal energy release at the core. This generated a fast-moving shockwave that raced outward, and this shock is what we now see as the outer boundary of the Rosetta bubbles, visible in X-rays as it heats the halo gas to millions of degrees. Driving this shock from behind was a powerful, magnetized wind of particles. This wind filled the interior of the expanding bubble, and its interactions are what produce the gamma rays seen by Fermi. The cooler, neutral hydrogen gas observed by radio telescopes represents a third component, denser material from the galactic disk that was caught up in the base of this outflow and swept along for the ride, much like dust and debris lifted by the shockwave of a terrestrial explosion. Together, they form a complete picture of a single, titanic eruption that involved hot shock fronts, energetic particle winds, and entrained cooler gas, all working in concert to reshape our galaxy's halo on a scale we are only beginning to appreciate. Yet, even as the dark matter halo dictates the grand motion of our galaxy, it presents us with a profound puzzle, a glaring mismatch between our most sophisticated theoretical models and the actual universe we observe. This is the missing satellite problem, a cosmic case where the clues don't match the crime scene. Our leading theory of the universe, the lambda-cold dark matter model, is spectacularly successful at explaining the large-scale structure of the cosmos. When cosmologists run supercomputer simulations of how dark matter should clump together under gravity, they produce a beautiful cosmic web of filaments and halos that looks just like the real thing. But these simulations come with a very specific prediction. The large halos that host big galaxies like our Milky Way should be swarming with thousands of smaller dark matter subhalos, the gravitational seeds for dwarf satellite galaxies. Yet when we look up at our own galactic neighborhood, we only see about 60 of these dwarfs. Where are the rest? Why is our sky not filled with thousands of tiny, faint galaxies orbiting our own? The first and most straightforward explanation is that our telescopes simply aren't powerful enough to see them. Many of these predicted subhalos could host galaxies that are incredibly faint, known as ultra-faint dwarfs. These are ghostly collections of a few thousand ancient stars, so dim and spread out that they blend almost perfectly into the background. It's like trying to spot a single, dim light bulb on a mountainside from miles away. In recent years, surveys like the Dark Energy Survey and Pan-STARRS have begun to find more of these ultra-faint dwarfs, slowly closing the gap between prediction and observation. But most astronomers agree that even with these new discoveries, we're still falling short of the thousands of satellites the simulations suggest should be there. This persistent discrepancy implies that the solution isn't just a matter of better technology. It might require us to tweak the properties of dark matter itself. This is where the physics gets truly fascinating. The standard model assumes cold dark matter, meaning the particles move relatively slowly. But what if dark matter is slightly warmer? Introducing warm dark matter is one of the most compelling theoretical solutions. In this model, the dark matter particles would have a tiny bit more thermal energy, meaning they would move faster in the early universe. This higher velocity would prevent them from clumping together on the smallest scales, effectively wiping out the formation of the very tiniest subhalos. The simulations with warm dark matter still produce large galaxies and the cosmic web, but they predict far fewer dwarf satellites, a result that aligns much more closely with our current observations. It's an elegant fix, but one that requires careful testing to ensure it doesn't break other successful predictions of the standard model. Another possibility is that the satellites aren't missing at all, they're just dark. The vast majority of those predicted subhalos could be completely devoid of stars. For a dark matter halo to host a visible galaxy, it needs to have attracted enough normal gas to form stars. But in the early universe, intense ultraviolet radiation from the first galaxies could have heated the cosmic gas, making it too hot to fall into the gravitational wells of the smallest dark matter clumps. Furthermore, the supernova explosions from the first stars could have blown any remaining gas clear out of these tiny halos, preventing them from ever lighting up. In this scenario, the Milky Way would indeed be surrounded by thousands of invisible dark matter subhalos, but they would be completely black, detectable only through their subtle gravitational influences, perhaps by distorting the light of more distant stars or through future, more sensitive experiments. The debate between these ideas is fought with incredible maps of the galactic halo. Astronomers compare the predicted distribution of dark matter subhalos from supercomputer simulations side by side with the actual observed positions of the known dwarf galaxies. In the simulations, the subhalos are arranged in a roughly spherical swarm, but the real dwarfs we've found seem to be arranged in that perplexing, thin rotating plane we discussed earlier, the vast polar structure. This spatial arrangement is another layer of the mystery. Not only are there fewer satellites than predicted, but the ones we do have are behaving in a way that the simplest simulations don't anticipate. This ongoing tension is a powerful driver for new technology. Upcoming telescopes like the Vera-C, Rubin Observatory are designed to conduct the deepest, widest surveys of the sky ever attempted, and they are expected to discover hundreds, if not thousands, of new ultra-faint dwarf galaxies. Their discoveries will provide the crucial data to finally determine if the missing satellites are simply too faint for our current eyes, or if we need to fundamentally rethink the nature of the invisible matter that holds our universe together. While the vast dark matter halo provides the gravitational anchor for our entire galaxy, astronomers have long wondered if this invisible ocean might have its own currents and eddies, subtle structures hidden within its overall form. This brings us to one of the most tantalizing and controversial ideas in modern astrophysics, the possibility of a ring of dark matter orbiting within the Milky Way. Imagine not just a smooth, spherical halo, but a dense, circular ripple of this mysterious material, a celestial ripple that could subtly warp the paths of everything around it. The first compelling, though indirect, evidence for such a structure came from a very specific and sensitive cosmic probe, a stream of stars known as GD1. Stellar streams are the ghostly remnants of small globular clusters or dwarf galaxies that have been torn apart by our galaxy's gravity. Their stars continue to orbit together in a long, thin line, tracing out a path that is exquisitely sensitive to any gravitational perturbations. Think of them as cosmic windsocks. Any breeze from a passing mass, visible or not, will make them wiggle. When astronomers mapped the GD1 stream in incredible detail using data from the Gaia spacecraft, they noticed something peculiar. The stream was not a single, smooth arc. It appeared to have gaps and a noticeable wiggle, a kink in its otherwise graceful trajectory. The most plausible explanation for this distortion was the gravitational influence of a massive object that had recently punched through the stream. But when they looked for the culprit, a massive globular cluster or a dark matter subhalo, there was nothing visible there. The only thing that could have caused such a pronounced effect was a significant, compact concentration of invisible mass. This led to the provocative hypothesis that a dense, clump-like ring of dark matter might have recently intersected the stream, its gravity acting like a cosmic pluck on a guitar string. Visualizing this interaction is key to understanding the claim. Sophisticated computer simulations show the process in action. You start with a perfectly thin, flowing stream of stars orbiting the galaxy. Then you introduce a massive, invisible object on a crossing path. As it passes through the stream, its gravity pulls the stars nearest to it slightly off their original course. This doesn't just create a single gap. It creates a characteristic pair of gaps and a visible offset in the stream on either side of the impact point, much like how a stone dropped into a flowing river creates a ripple and a dip in the water's surface. The detailed structure of the wiggle in GD1 matches this simulated signature remarkably well, suggesting a recent encounter with an object boasting the mass of 1 million suns, yet completely undetectable by any telescope. However, the scientific community is far from unanimous on this interpretation. The challenge of confirming such a subtle feature is immense. The primary obstacle is that we are trying to map the invisible using only the most delicate of tracers. Other factors could potentially mimic the observed effects. Perhaps the stream was born with that irregularity, a relic of the internal dynamics of its parent cluster as it was being torn apart. Maybe the perturbation was caused not by a single, large dark matter clump, but by a smaller, visible object like an intermediate mass black hole that we simply haven't spotted yet. Or the gravitational influence could come from the collective, lumpy nature of the dark matter halo itself, rather than a distinct ring-like structure. Proving the ring hypothesis requires ruling out all these other possibilities, a task that demands more data, more streams, and even more precise measurements. The search for corroborating evidence is now a major focus. Astronomers are scouring other stellar streams like the Phoenix Stream and Gelum, looking for similar patterns of gaps and wiggles that might betray the presence of other dark matter rings or substructures. They are also running ever more detailed simulations to model how different types of dark matter, whether cold, warm, or something else entirely, would clump together and interact with these streams. The presence of numerous such rings would strongly support the cold dark matter model, which predicts a universe teeming with these dark satellites. Conversely, if such features remain rare, it might point toward warmer, faster-moving dark matter particles that resist forming small-scale clumps. Ultimately, the hunt for a dark matter ring is a beautiful example of astronomical detective work at its most challenging. It involves using the faintest of clues, the slight deviation in the path of a string of ancient stars, to infer the architecture of the invisible universe. Whether the evidence from GD1 holds up or is eventually explained away, the investigation itself pushes our methods to their limit, forcing us to develop new tools and new ideas to illuminate the dark components of our cosmos. It's a reminder that even the most dominant force in our galaxy can leave behind the most delicate of fingerprints, if only we know how to look for them. After contemplating the grand, invisible architecture of dark matter and the subtle ripples that might move within it, we now turn to a class of objects that are almost the exact opposite: supremely dense, incredibly bright, and deceptively small. These are the ultra-compact dwarf galaxies, or UCT, celestial entities that defy simple classification and present a fascinating puzzle in our understanding of how stellar systems form and evolve. They represent a strange and extreme corner of the cosmos, where the definitions of a star cluster and a true galaxy begin to blur into irrelevance. The story of their discovery is a classic tale of astronomical resolution. For decades, when astronomers looked at dense clusters of galaxies like the Fornax cluster, they would see the giant elliptical galaxies and, dotting the space around them, what appeared to be large, bright globular clusters. These were considered nothing more than ancient, spherical collections of stars orbiting the larger galaxies. However, as telescope technology advanced, particularly with the keen eyes of the Hubble Space Telescope and powerful ground-based observatories, researchers could resolve these star clusters with greater precision. They began to notice that a certain population of these objects was peculiar. They were far too luminous and massive to be ordinary globular clusters. A typical globular cluster might contain a few 100,000 stars. These new objects were shining with the light of tens of millions of suns, yet they were packed into a region of space only about 200 light-years across. That's roughly the distance from our Sun to the famed Orion Nebula. To hold so many stars in such a tiny volume is an astonishing feat of cosmic density, and it immediately set these objects apart as a new, distinct class, the ultra-compact dwarfs. To truly grasp their bizarre nature, consider a simple size comparison. Our own Milky Way is a majestic spiral roughly 100,000 light-years from end to end. A large globular cluster like Omega Centauri is a dense sphere about 150 light-years in diameter. An ultra-compact dwarf galaxy splits the difference in the most extreme way imaginable. It has the stellar mass of a small dwarf galaxy, enough to form a recognizable cosmic entity, but it is crammed into a physical space only slightly larger than a big globular cluster. This results in a stellar density that is almost incomprehensible. If you were standing on a planet orbiting a star in the heart of a UCD, your night sky would be a breathtaking and perhaps terrifying spectacle. The sky would be filled with tens of thousands of stars brighter than Venus appears from Earth, all separated by distances that are, on a cosmic scale, shockingly intimate. It would be a perpetual, brilliant twilight with stars so close you could almost reach out and touch them. This incredible density is the source of their greatest mystery. How did they form? Astronomers have two leading and very different theories. The first is known as the threshing scenario. This theory suggests that UCDs are not primordial objects at all, but the stripped-down, skeletal remains of larger dwarf galaxies that ventured too close to a giant galaxy. Imagine a small galaxy with a central bulge and a loose halo of stars. As it swings past a gravitational titan like a giant elliptical galaxy, the immense tidal forces act like a cosmic threshing machine. The outer layers of stars, loosely bound by gravity, are effortlessly peeled away and scattered into the cluster. What remains is only the small, incredibly dense nucleus of the original galaxy, which is now so tightly bound by its own gravity that it can withstand the tidal forces. This nucleus, having lost its fluffy exterior, is now revealed as an ultra-compact dwarf. This is a compelling story of galactic cannibalism, where the victim is reduced to its barest, most resilient core. The second theory proposes a more direct origin. Perhaps UCDs are simply the most massive and dense examples of globular clusters, the natural upper limit of how a bound group of stars can form. In the turbulent early universe, regions of especially dense gas might have collapsed to form these superclusters in a single, massive burst of star formation. They would be born ultra-compact, representing the peak of stellar system density right from their inception. This theory is supported by the fact that some UCDs, like the magnificent M60 UCD1 in the Virgo cluster, harbor astonishing surprises that tilt the scales. This particular UCD was found to contain a supermassive black hole at its center, a black hole that makes up a staggering 15% of the entire galaxy's mass. The presence of such a massive central engine is a hallmark of a true galaxy, not a star cluster, and provides powerful evidence for the threshing scenario, as it's easy to imagine this black hole was once the central anchor of a much larger system. The study of these objects is far more than just an exercise in cosmic taxonomy. UCDs serve as unique natural laboratories for testing the laws of dynamics and gravity in environments of extreme stellar density. They allow astronomers to study how stars interact and behave when packed together like sardines in a can, a situation that can lead to exotic stellar collisions and the formation of strange binary systems. Furthermore, their existence challenges our definitions. At what point does a large star cluster become a small galaxy? Is the presence of a supermassive black hole the deciding factor, or is it the sheer weight of stars? Ultra-compact dwarf galaxies sit squarely on this boundary, forcing us to refine our categories and acknowledge that the universe is under no obligation to create objects that fit neatly into our boxes. They are a brilliant, dense, and enigmatic reminder that sometimes the most extraordinary things in the cosmos come in the smallest, most unassuming packages. But for all their incredible density and strange origins, ultra-compact dwarfs are still bound by the same fundamental forces as everything else in the galaxy, governed by gravity and moving along predictable paths. What if you needed to navigate those paths with absolute precision across the unimaginable voids between stars? This brings us to a network of celestial lighthouses so reliable and steady that they form the framework for a potential galactic positioning system, a navigation network that could guide a ship across the entire Milky Way. These are the millisecond pulsars, and their mind-boggling regularity makes them the most accurate clocks in the universe. A pulsar is the rapidly spinning, ultra-dense core of a star that has died in a supernova explosion. As it rotates, it shoots out beams of radiation from its magnetic poles. If those beams sweep across Earth, we see a regular pulse of light like a cosmic lighthouse. Most pulsars slow down gradually over millions of years, their rhythms slowly fading. But a special class known as millisecond pulsars have been brought back from the brink. These are old pulsars that have been spun up to incredible speeds by a companion star. In a binary system, the pulsar's immense gravity can pull material from its partner. As this gas spirals onto the pulsar, it transfers angular momentum, acting like a cosmic starter motor that cranks its rotation up to hundreds of times per second. Once the companion star is consumed or disrupted, the pulsar is left behind, spinning at these phenomenal rates with a stability that rivals the most advanced atomic clocks we can build on Earth. This breathtaking regularity is their most valuable feature. Their pulses are so predictable that we can calculate when each one should arrive to within a fraction of a microsecond, years or even decades into the future. This makes them perfect celestial milestones, the concept for a galactic GPS, often called pulsar-based navigation or PNT pulsar timing navigation, works on a simple principle of triangulation, not unlike how our Earth-based GPS functions. A spacecraft would carry a highly sensitive X-ray telescope, By carefully monitoring the arrival times of pulses from at least 3 different known millisecond pulsars, the craft's onboard computer could compare the actual time a pulse arrived with the time it was predicted to arrive. The tiny difference between these times reveals the light travel time from the pulsar to the spacecraft. Since the precise location of each pulsar in the galaxy can be mapped, these minute timing differences can be used to calculate the spacecraft's position in 3-dimensional space with astonishing accuracy, potentially down to a few meters, anywhere in the solar system and eventually beyond. The real-world application of this technology is already being tested. NASA's groundbreaking NICER experiment aboard the International Space Station has successfully demonstrated this very principle. The station's Sextant project used timing data from millisecond pulsars to autonomously determine the ISS's position in orbit, proving that X-ray pulsar navigation is not just science fiction but a viable technology for future deep space missions. This system would provide a crucial backup for crewed missions to Mars and beyond, offering a self-contained navigation source that doesn't rely on signals from Earth, which can take minutes or hours to travel one way. But the utility of these cosmic clocks extends far beyond navigation. Their incredible precision has given rise to ambitious international projects known as pulsar timing arrays. These initiatives, like the North American Nanohertz Observatory for Gravitational Waves (NanoGrav), use widely spaced radio telescopes to monitor an entire network of these millisecond pulsars for decades. They are not listening to single pulsars, but rather looking at the network as a whole, searching for a specific, correlated pattern in the timing residuals, the tiny discrepancies between predicted and actual pulse arrival times. The hypothesis is that a passing gravitational wave, a ripple in the fabric of spacetime caused by the collision of supermassive black holes, would minutely stretch and compress the space between Earth and the pulsars. This would cause the pulses to arrive systematically early or late in a way that correlates across the entire array. Visualizing this data often involves a spaghetti plot of timing residuals for dozens of pulsars. The quest is to find a low-frequency hum, a gravitational wave background that affects all the pulsars in the array in a coordinated way, a signature that would be unmistakable evidence of the universe's most colossal events. The pursuit of this signal is a testament to patience and precision, requiring years of meticulous data collection to separate this faint cosmic whisper from the noise. A recent analysis of over 12 years of nanograv data has revealed a promising common signal across dozens of pulsars, a potential first hint of this gravitational wave background, though confirmation is ongoing. This incredible endeavor turns the entire galaxy into a gravitational wave observatory, using these dead stars as the markers and the space between them as the detector. It shows us that the same pulsing beacons that could one day guide our ships between the stars are also our ears to the cosmos, listening for the echoes of its most violent and ancient collisions. Yet for all the precision of pulsar clocks and the vast architecture of dark matter, some of the Milky Way's most enduring mysteries are written not in gravity or time, but in the language of chemistry, etched into the clouds of gas that drift between the stars. We now arrive at a puzzle that is both universal and curiously specific, the strange and unexplained behavior of a simple molecule that should be utterly commonplace, carbon monoxide. This humble combination of one carbon atom and one oxygen atom is the second most abundant molecule in space after hydrogen, and for decades, astronomers have relied on it as their primary tool for mapping the invisible. Yet, the more we look, the more this trusted guide reveals a distribution so bizarre and inconsistent that it forces us to question our most fundamental understanding of interstellar chemistry itself. The story begins with a fundamental problem in astronomy. How do you see something that is determined not to be seen? The vast reservoirs of molecular gas, the raw material for new stars, are primarily made of cold, dense hydrogen molecules. But hydrogen molecules are notoriously difficult to detect directly in the frigid environment of a molecular cloud. They simply don't emit or absorb light in a way that's easy for our telescopes to pick up. Carbon monoxide, however, is different. Its structure allows it to rotate, and as it does, it emits light at very specific, predictable millimeter wavelengths. This makes it shine like a tiny beacon in the radio silence of deep space. For over half a century, radio telescopes have scanned the skies, tuning into this specific emission line to trace the outlines of the Milky Way's hidden bones, painting a picture of the cold, dark clouds where stars are born. The famous Columbia Center for Astrophysics CO survey of the Milky Way in the 1980s was one of the first to reveal the full spiral structure of our galaxy, not by its stars, but by this molecular gas using carbon monoxide as its proxy. This all seems perfectly logical, but the mystery arises from the underlying assumption that the amount of carbon monoxide we see is a direct and reliable indicator of the amount of molecular hydrogen present. Astronomers use a value called the XCO factor, a conversion factor that translates the observed intensity of CO emission into an estimated quantity of H2. For decades, this factor was treated as a cosmic constant, a fixed rule of thumb used to weigh entire galaxies. But as our telescopes became more powerful, allowing us to peer into individual clouds with greater resolution, a troubling pattern emerged. The relationship between carbon monoxide and hydrogen was anything but constant. In the diffuse outer regions of molecular clouds, and especially in the low metal environments of dwarf galaxies and the galactic halo, the CO emission drops off precipitously. In these regions, the intense flood of ultraviolet radiation from nearby stars, known as the interstellar radiation field, can easily break apart the fragile CO molecule. This creates vast CO-dark molecular gas reservoirs where the hydrogen is present but its traditional tracer has been destroyed, leading to a massive underestimate of the galaxy's true molecular mass. Conversely, and even more puzzlingly, there are places where carbon monoxide appears to be inexplicably overabundant. Detailed maps from instruments like the Atacama Large Millimeter Array, or ALMA, reveal intricate structures within nebulae like Orion. These maps show vibrant, swirling clouds of CO, but they also reveal bright, sharp-edged clumps and filaments where the CO emission is far more intense than the background molecular gas should allow. This suggests that in these specific, shielded environments, perhaps deep within the densest cores of clouds or on the protected sides of dense filaments, some unknown process is either producing CO with freakish efficiency or protecting it from its usual destructive fate. The chemistry within these clouds is a frantic dance governed by extreme conditions. CO forms on the surfaces of tiny dust grains where atoms can meet and bond and is then released back into the gas. But in these bright clumps, the standard models of gas phase and surface chemistry struggle to account for the observed concentrations. It's as if we've walked into a factory expecting a steady production line and instead found stockpiles of finished goods with no clear explanation for how they got there. This isn't just an academic curiosity, it strikes at the heart of how we understand the life cycle of galaxies. If we cannot accurately measure the amount of raw material available for star formation, our predictions for how galaxies evolve are built on a shaky foundation. An over-reliance on CO without understanding its quirks could lead us to believe a region is poor in star-forming gas when it is actually rich, or vice versa. The solution likely lies in moving beyond a single tracer. Modern astronomers are now building a more complete toolkit, searching for alternative, fainter molecules that can probe these CO-dark regions, such as using the emission of ionized carbon or even tracing the dust grains themselves. Each new molecule adds a piece to the puzzle, helping us create a three-dimensional picture of the interstellar medium that is far more complex and chemically diverse than we ever imagined. The mystery of galactic carbon monoxide is a powerful lesson in cosmic humility. reminding us that even the most trusted tools in our kit can hold hidden complexities, and that the universe's simplest recipes often have the most surprising ingredients. But just as the chemical makeup of interstellar gas reveals hidden complexities, the space between the stars is not an empty void. It is threaded by an invisible force that shapes the journey of every charged particle and guides the birth of new solar systems. This brings us to our final and perhaps most pervasive strange object, the galactic magnetic field, an invisible architecture woven through the entire Milky Way. We often picture our galaxy as a collection of stars, planets, and gas, governed solely by gravity. But gravity is only part of the story. A vast, ordered magnetic field permeates every corner of our galactic home, a force so subtle we cannot see it, yet so powerful it directs the flow of cosmic violence and the collapse of stellar nurseries. Mapping this invisible force requires ingenious tricks of observation, and one of the most powerful techniques relies on a property of light called Faraday rotation. As light from a distant quasar or pulsar travels through the Milky Way, it passes through magnetized clouds of electrons. The magnetic field within these clouds causes the direction of the light's wave to slowly rotate, like a screw turning as it moves through a threaded hole. By precisely measuring this rotation across thousands of distant sources, astronomers can work backwards to create a three-dimensional tomographic map of our galaxy's magnetic field. The visualizations created from this data are stunning and revealing. They don't show a simple north-south orientation like a bar magnet. Instead, they reveal a complex and ordered tapestry. The field lines largely follow the spiral arms of the galaxy, but they are also punctuated by turbulent bubbles, reversals in direction, and vast, coherent structures that stretch for thousands of light years. It's a hidden skeleton of magnetic force, giving shape and structure to the apparently chaotic interstellar medium. This magnetic framework is not a passive observer. It is an active player in some of the galaxy's most dramatic processes. For high-energy cosmic rays, protons and atomic nuclei accelerated to near-light speed by supernova explosions, the galactic magnetic field is a chaotic maze. These charged particles cannot travel in straight lines. They are forced to spiral along the magnetic field lines, bouncing and scattering in all directions. This magnetic maze effectively traps cosmic rays within the galaxy for millions of years, preventing them from simply flying off into intergalactic space. It also makes their origins incredibly difficult to trace back, as their paths are scrambled beyond recognition by the time they reach our detectors. Without this magnetic containment, the intense radiation environment of our galaxy would be vastly different. On a grander, more creative scale, these magnetic fields are also the unsung architects of star formation. A collapsing cloud of gas has a tremendous amount of rotational energy. If left unchecked, this spin would fling material outward and prevent a star from ever forming. This is where magnetic fields provide a crucial braking mechanism. The field lines threading through the cloud get dragged inward as it collapses, and like elastic bands being stretched, they build up tension. This tension transfers angular momentum away from the central core and out to the wider cloud, allowing the dense heart to continue collapsing into a protostar. In essence, the magnetic field acts as a cosmic governor, regulating the spin of a nascent star system and enabling the birth of new suns. It is a fundamental ingredient without which the galaxy would be a much darker and quieter place. Yet for all we understand about its effects, the origin and maintenance of this galaxy-spanning field remains one of astrophysics' great unsolved puzzles. The most widely accepted theory is the dynamo effect. This proposes that the slow, differential rotation of the galaxy, the inner region spinning faster than the outer one, somehow stretches and twists any small, primordial magnetic seed field, amplifying it over billions of years into the organized structure we see today. It's analogous to how a simple bicycle dynamo converts rotational motion into an electrical current, but on a mind-bogglingly vast scale. The charged particles and turbulent motions within the galactic disk provide the conductive fluid and the complex motions needed to sustain this cosmic generator. However, the details are maddeningly complex. How was the initial seed field created? What exactly sustains the dynamo against the natural tendency of magnetic fields to decay and dissipate? Competing theories suggest that outflows from supernova or even the active galactic nucleus could play a role in continually injecting energy and order into the magnetic system. The truth is, we are still grappling with the fundamental physics of how such a large-scale, coherent field can be generated and maintained within the turbulent, chaotic environment of a spiral galaxy. The galactic magnetic field is a silent, pervasive, and powerful force that has shaped the evolution of our cosmic home, a final enigmatic structure proving that the universe's greatest wonders are often those we can only infer, not see. And so our journey through the Milky Way's menagerie of mysteries comes to a close, but the story of discovery is far from over. From the invisible, galaxy-tugging pull of the Great Attractor to the ghostly, star-forming wake of a runaway black hole, we have encountered a cosmos that is infinitely stranger, more violent, and more beautiful than we could have ever imagined. These 30 objects are not just a list of curiosities, they are a testament to a fundamental truth about our universe. For every question we answer, a dozen new, more profound puzzles emerge from the darkness, each one challenging our assumptions and pushing the boundaries of our understanding. This incredible diversity, from the perfectly geometric artistry of the red rectangle to the chaotic, predatory nature of the Black Widow pulsar, shows us that our galaxy is not a static museum piece. It is a dynamic, evolving, and often violent ecosystem. It is a place where entire galaxies are consumed, where black holes are sent careening into the void, and where the vast majority of the substance that holds it all together remains completely invisible to us. These wonders are not distant, abstract concepts. They are the very fabric of our cosmic home, happening right here, right now, in our own galactic backyard. The ongoing effort to solve these puzzles is a grand, collaborative human endeavor. It is powered by the sharp eyes of space telescopes like Hubble, Webb, and Gaia, by the immense listening ears of radio arrays like Mir-KT and Olma, and by the brilliant, curious minds of scientists around the globe. But it is also fueled by the awe and curiosity of everyone who has ever looked up at the night sky and wondered what's out there. Every new observation, every sophisticated computer simulation, and every revolutionary theory brings us one step closer to peeling back another layer of the cosmic onion. So as we conclude this tour of the strange and wonderful, I encourage you to carry this sense of wonder with you. The next time you find yourself under a clear, dark sky, look up at that faint, milky band of light and remember the incredible secrets it holds. Remember that the universe is not finished surprising us. Stay curious, keep asking questions, and never stop looking up. I'd love to hear which of these strange objects captured your imagination the most. Was it the haunting perfection of Hoag's object, the terrifying power of the hypervelocity stars, or the pervasive mystery of the dark matter halo? Let me know your thoughts in the comments below. And if you're hungry for more journeys to the edge of understanding, make sure to subscribe and hit the bell so you don't miss our next exploration into the deepest mysteries of the cosmos. The universe.